So first off, thanks for everybody for coming. Hope this session turns out to be a productive, useful knowledge transfer for everyone, learning session. This tutorial is network analysis made simple. I've taught this since 2015, so it's 10 years running now. Every year I try to deliver it somewhere, right, and try to share the knowledge that I've gained over the years. I built this tutorial because in grad school, 2014, I was working with networks as a data structure, as a model for my thesis, which was in influenza, evolution, and ecology. And I knew I needed to learn that speed run learning about applied network science and graph theory. And so the best way to learn something is to teach it. I forced myself to put together this tutorial, basically first for myself and then as a gift back to the scientific Python community, which I had benefited from for many years. And so this is the product of a lot of that learning, and it's been refined over the years as well as I learn new things, interact with others within the scientific Python community and the likes. Maybe another point that I'd like to make is that the Python tooling world has also evolved over the years. Conda has played a big role in our community for a long time, and recently Pixie and UV showed up as new package managers, and I decided this year was the year that I would like to introduce UV and Pixie, primarily UV in this case, for single notebooks to folks, just to give everybody a little bit more of a muscle memory or that sort of exposure to the tooling. One of the key advantages of using UV with, say, Marimo notebooks, which is what we're using this year, is that UV allows us to have Python shipped to us based on our definition of what Python we need, rather than us trying to wrangle everything within a single environment that has a Python that we have, right? So Peter Wang was the guy who articulated this point most clearly in a talk on that's recorded on YouTube, which is basically, let me get you the Python you need, rather than let me ask what Python you have, right? And that's what UV and Pixie are both capable of. And if you missed yesterday's Pixie tutorial, I'd strongly encourage go catch up on it on YouTube. It was an excellent tutorial for understanding how to use Pixie, which both of them, Pixie and UV, have the same philosophy there. Okay, I want to do a quick pulse check. How many of you are done with setup? That is, you have UV installed. That literally is all that you need. If you have UV installed, that's good. And how many of you have managed to launch this notebook by following these instructions? Can I get a thumbs up? So you should see this over here. And I'll just note for the rest of this tutorial, remember this pattern where we're going to cd into a notebook directory, and then we're going to UVX Marimo edit sandbox mode sum.py file. And those instructions should be available on the README of the Git repository in a more generic form. So I don't do it for I'm not that prescriptive for every single notebook. But if you can remember this for every single for each notebook that we'll work through, then that should do the trick. There's one other change that I want you to make note of, which is as soon as you've launched this notebook, I'd like you to toggle 3 settings on Marimo. So at the bottom, I'd like you to toggle on startup auto run. So just click on that, and it'll switch to lazy mode. And then on cell change, disable that as well. And on module change, also toggle that to lazy execution. So what's the rationale for this? So one of the features of Marimo notebooks is that they are eagerly executed. And what that means is if you make a change in a cell that has dependent cells, uses a variable or calls on a function that was defined in a previous cell, Marimo will automatically, in auto mode, it will automatically execute the dependent cells as well. And what this does is it has the effect of preventing your notebook cell's state from going out of sync, out of date, right? We know that from, again, the Jupyter world was part of our lives for many years. I was a heavy Jupyter notebook user, but I always fell into that trap of I redefine a variable upstream, and I forgot that I redefined that variable, and so then now I need to be careful about the state of my notebook. And so auto mode does that. However, for teaching purposes, just for today, I want to re-enable lazy mode, which mimics Jupyter Notebook behavior. And what that will allow is it'll prevent me from having a notebook that has all the outputs already like pre-computed, and it will allow for a little bit more interactivity. So at the minimum, you'll get to hit Command Enter or hit the play button on a cell to see the outputs, right? So it's less automatic that way. It's a little bit more engaging that way for teaching purposes. I noticed from yesterday's tutorial, which I was teaching, the notebooks just executed, and I ended up monologuing a lot without a lot of interactivity enabled for everyone. So I just want to make sure you have these three modes: auto run lazy, on startup lazy, on cell change lazy, on module change lazy, just to make sure you have non-automatic execution of code, right? And so then that way you get a little bit more interactivity. I saw a question there.
Yes, if I have Marimo installed locally,
Yes.
is there any reason to not call it directly instead of using UVX?
Oh, good question. So the question was, if you have Marimo already installed locally, is there a reason to just use UVX? The answer is no real reason, because if you've got the latest version of Marimo, then feel free to just use Marimo directly. You don't need to use UVX Marimo. UVX allows you to install Python tools without allows you to run Python tools without ever installing them. And so I've just muscle memory defaulted to UVX, so I never have to carry the state information of like what exactly was installed on my system. I'm just always running the latest, right? So that's something that has its pros and cons, but for me, I'm willingly accepting the cons for the pros. Okay. Any other questions?
I won't ask too many questions about UV, but you have to install somewhere, right?
Yes.
It's just in a cache folder somewhere.
Yes. So you mean the packages that are pulled in, or do you mean?
Marimo is now on my computer somewhere.
That's right. It's living somewhere. So that's right. So the question was, when we do UVX Marimo, like it's going to get pulled down somewhere. It's not executing out of thin air. That's right. So we're actually caching it inside a local directory on your machine, and then running the executable from that directory, from the cache directory itself. Okay, cool. Any other questions on this so far? Cool. So for those who just joined, please ask one of your neighbors for installation instructions or on how to get set up. Literally, it should be merely install UV for those who don't have it already, and that should be enough for today. Cool. All right, so that's a little bit of the logistics. I'm going to actually switch off this notebook now and change to a different notebook. So the way to do this, I'm going to close the tab, and then I'm going to come back to Network Analysis Made Simple. Switch back my language. Cool stuff. So right now, UV is running. I can't do clear. Control C, yes, enter. That will let me exit the Marimo session, Marimo server process, sorry. And so what we're going to do next, because my current working directory is the notebooks and 00 preface over here. I have another notebook. Ooh, it's a little tough to read. I have another notebook that is called 02 prereqs and 03 goals. I'm going to skip the prereqs because really the prereq for this course is you can write Python, and if you can write a for loop. If conditionals, yeah, if you can do conditionals, you can do looping, you're fine. The third thing so I'm going to skip over to notebook 3. So let's do it. UVX Marimo edit sandbox 03 goals.py. You may notice that they're like companion.md or .ipynb files. Those are legacy. I'm just in the process right now of like moving all the content over into Marimo notebooks. So let's hit enter. And that should load up over here. And you'll notice none of this has executed, which means lazy mode is on, which is perfect. So that means I am going to need to start to execute some cells. So I'm going to hit the play button. And the play button on the bottom right-hand corner will actually end up executing all cells for me. And so, all right, but thankfully this is all just Marimo markdown cells. So there's nothing to execute. All right, so first off, this tutorial, Network Analysis Made Simple, after all that spiel about setup and the likes, I got some technical takeaways for everybody today. The first is, if you've never used the NetworkX API, hopefully this becomes a friendly introduction to NetworkX for you. I've chosen NetworkX as the package of choice because its API is very friendly for beginners, and its API also matches graph theory concepts very closely. So if you learn how to do something in NetworkX, and then you go and read some article or paper on how it works in graph, some more theoretical papers, it should be not too difficult to match up. Second takeaway is that of, let me see if this works, visualization. So if you want to be able to do graph visualization in a way that doesn't involve hairballs, my hope is we introduce you to some of the concepts of rational graph visualizations. The third thing that I'd like you to understand is basic graph algorithms. So how to think about problems in a way that involves the relationships between nodes, and finding things like special graph structures or finding paths in a graph and that sort of stuff. And this will help broaden your ability to interact with graph data structures. And if we have the time there, then I might have the ability to show some notebooks that show a bit of the connection between graph theory and other areas of math, or computing, such as stats or linear algebra and the likes. And I think that could be something cool to see. If we don't have time, nonetheless, the notebooks are available for folks to explore on your own. And at the top of almost all of the notebooks, I have a YouTube video where I sat down and recorded myself doing an overview. So this is also self-paceable. You can go back home and look through those videos as well. Cool. So those are the technical goals for the tutorial. And then there are some intellectual goals as well. How many of you are data scientists who work frequently with tabular data? I would raise my hand as well, right? This is tabular data are common, and but what gets interesting is if your tabular data, like your entities are usually your rows in your table. Where it gets interesting is if there are relationships to model between the rows in your data. And if there are relationships, then that's what makes it kind of interesting. Like, let's say you have you might be operating a social network of some kind. Your nodes might be the people in there, so you might have tabular data about the people. But what about how they're interacting? That's where interesting stuff happens, right? And so we talk a lot about relational insights. That's what we mean by relational insights. And then, of course, the other thing to do is to understand how to think on graphs. And what I mean by this is as follows. Just to anchor it a little bit, if I were to tell you, if I were to give you, here's a graph, find me the shortest path between these two nodes, you, with a human visual cortex, you could just go, yeah, it's that path, right? You could do that. But that's not how a computer works, right? For a computer to work, it does not have the full visual view of the entire graph. You have to actually think algorithmically step by step of what should be happening next. And so this is where algorithmic thinking becomes a muscle to develop. I trust most of us here do have it, but it becomes extremely important if you're dealing with graphs, because computers can't solve problems necessarily the way that humans do. All right, so I'm gonna stop here for a moment. I'm gonna ask if there are any further questions about the goals, or if you have any other setup questions, let me know as well. Any questions? Looks like not. Okay. Eric, was there something just now, like a problem that was happening over there, or is everything okay? Working on it? Okay, cool. Okay, so if you've got set up, great. If you aren't set up yet, I'd strongly encourage, it's perfectly okay to pair code with someone else. And if even that is not working out for you, this tutorial does involve some more intellectually demanding components. But those, if you're well equipped with programming skills, you should be able to do them on pencil and paper. Or you can just chill in your seat, relax, enjoy the show. That also works out as well. Okay, so actually let me just close all of that. And then let me switch over to a different notebook. We're going to cd out of this directory. I'd encourage you to do the same as well. And we're going to cd into 01 introduction. And then we're going to launch 01graphs.py. UVX Marimo edit, sandbox, -- sandbox, 01graphs.py. You should be ideally in the directory to launch the notebook. That will launch. All right, cool. Yeah, this is lazy loading at its best. So I need this to run. There's the notebook. There's the YouTube video, sorry. Then we have some of these other guys down here. Okay, so let's get started. Actually, you know what? I'm just gonna run all the cells. I'm gonna run all the cells. This one is okay to run all the cells. Cool. Let's think about, actually, before we go on, this is a class about networks. We're here for a conference. You should network. So go introduce yourself to your neighbor. Behind you, in front of you, to your left, to your right. Okay, alrighty. So we've made little networks, haven't we? Let's talk about what networks are. Networks, at its core, are comprised of two sets of objects. This is a little bit more on the mathematical side. The two sets of objects, and I'm being very, very intentional here. It's sets, not lists, which means uniqueness is a very important property here. So you got two sets of nodes. You've got the node set and the edge set. So that's these guys over here. So for example, you might have a set over here that is set n for the nodes and has unique elements A, B, C, D. And then you would represent the edge set something like this, as E is equal to a tuple of nodes, like tuples of nodes. So you have unique pairs of nodes that exist between one another. In the networking that we just did, could I get some popcorn-style feedback, right? Who or what were the nodes and what were the edges? I'm a node. You're a node. I'm a node too. Anybody else is a node? We're all nodes, right? People here are the nodes. And what about the edges? What defines the edges? So I'm hearing a few things. I hear connection, conversation. So it could be that you are connected by proximity. It could be that you are connected by the fact that you had a conversation. What else is there? Qualities like location. Oh, okay. So you two people sharing the same geographic home base, for example, right? Like that is another definition of an edge that we could have amongst people here. Anything else? We might work at the same company, for example. That's another one, right? So relationships define the edges between nodes. And one thing that I hope will become clear by the end of the tutorial is that how you define the relationship really matters for how you end up modeling. And we'll walk through a few examples in a moment as well. Okay. Let me see if this actually works. I want to draw. Yeah, if you guys know Vincent Warmerdam, on YouTube, and he works for Marimo, and I recently bought for myself a little cheap tablet with this and bought Screen and Draw. So it was like $50 for the tablet and $4 for the software, and now I can draw on the screen at will. I'm trying this out as an experiment. So this year's the year of experiments and tutorial settings. Okay, so you might draw graphs like this, right? You've got circles and a line between them. That's usually the most canonical way that we draw graphs out on a screen. And this is what I mean by, like, you can actually draw out a graph or draw out a network, and the human visual cortex can do a lot of very implicit solving, right? Like on solving certain problems on these graphs. Okay, cool. I'd like you all to probably I'd like you all to go and discuss with your neighbor now examples of networks that you've seen in either your day-to-day life or in your work setting, right? So go ahead, spend 2 minutes, 3 minutes, talk with your neighbor about that. Okay, we're at 3 minutes-ish. Let's come back together. Love the discussion. Let's keep this energy level for today as well. I'd love to hear from everybody. What are some examples of graphs that you've seen in your profession, in your day-to-day life? Popcorn style. Any takers?
In a factory.
In a factory, what are the nodes and what are the relationships?
Sensors.
Sensors are nodes.
And then you're trying to see how proximity to sensors. So when something goes wrong, you can detect what part of the factory.
Oh, wow. Okay, so you might have a sensor network that's deployed in a factory, and you would have incidents happening on the machines in a factory, and then you could then create a map between the incident and the closest sensors, or you can actually map the distance from the incident to the sensors and use that as a way to triage where to go to solve, go and send some people down, right? Okay, cool. So this actually is a unique graph that has two sets of nodes. you have the sensor nodes and you have the incident nodes. Like the entity is like the two entities sets here. And we'll talk about it, or it's discussed later in a later notebook called bipartite graphs. And now you have relationships that are defined between the incident and the sensor itself. So that's a cool example. All right, I think I saw a hand on this side. Love it. I'm a biologist. Yes. So what are the nodes and what are the edges?
Nodes would be various proteins, and the edges are the functions that each of these proteins have.
The interactions, you mean, right? Yes, the interactions between them. Yes, exactly. And now, one thing that I love about this example, not only because it's from my own native training, but also the term interaction is actually a nebulous term, right? Because what exactly do we mean by a protein-protein interaction? Do we mean that they're actually physically touching each other in a cell? Or do we mean that the presence of one gene downregulates another, right, through transcriptional activity or the likes? How we define an interaction changes how we might solve our problem at hand, right? And so this is an example where being very specific about the definition of an edge becomes very, very important. Because if I'm talking about gene regulatory networks, I am not really caring so much about whether two proteins are interacting with one another unless they are part of a gene regulatory network, right? Okay, cool, great. Any other examples? More pedestrian examples or more advanced examples?
That notebook.
Oh, tell me about it.
It's the nodes are the cells.
Yes?
The edges are depends on relationships.
Oh, perfect. Yeah, okay, so we'll see it later. Marimo notebooks themselves are graphs of notebook cells. And in this particular case, I have no dependencies, but I do have nodes. But you'll see in later notebooks, if you opened up the Explore Dependencies tab on the left-hand side here, you might actually see that certain cells are dependent on one another. And so yes, the nodes are the cells and the edges are dependencies based on what variables are exported from a cell. Anything else? Back there. ATM, sorry? ATM fraud. Tell me more. Yes? The nodes are the individuals. Okay, cool. That is another example of a bipartite graph. This session is more advanced than I've ever seen before. We've gone to bipartite graphs 2 times already. That's awesome. Yes, so location is a node type, and then people are another node type, and we define an edge between them. You'll notice we don't explicitly, in this formal definition, define a relationship between nodes of the same type. They're defined across types, but there's a way to project, as we'll look at later, or have a chance to, if we have a chance to look at later, there's a way to project it onto one of the partitions of the, one of the node sets and use that for, solving other problems as well. Okay. Let's talk about LinkedIn versus Twitter. Because I think those are social networks. I guess we've all gotten so used to social networks, we rarely think about them as networks anymore. But they are prevalent in our life, and hopefully everybody here gets to network with other people on LinkedIn and build your network there as well. What's the difference between LinkedIn and Twitter in terms of the relationship definition?
It's kind of like a one-way graph, you can't always talk to people, but you follow them on LinkedIn, it's kind of all over the place.
Right. So there's a fundamental difference in the definition between a connection on Twitter versus a definition of a connection on LinkedIn. On Twitter, I can follow someone else. And that person doesn't necessarily have to follow me. So that is one definition of a connection on Twitter. There is another definition, which is I can tweet at someone on Twitter, but they may not necessarily be able to reply to me, right? So that is another thing as well. Whereas on LinkedIn, what's the difference with LinkedIn then? Exactly. You're either connected or you're not connected. So there is a directionality that occurs on Twitter that may not necessarily be modeled on LinkedIn. Does everybody make sense? Yep. Yes. Now, if we do think about the follow functionality on LinkedIn and we consider that graph, then yes, we have an asymmetric connection over there. So people might follow other people without explicitly connecting. That's actually a good point. So Twitter, LinkedIn used to not have that functionality, right? But then must have added it within the last few years. I haven't paid too close attention. So that's actually a good point. It's a good point. So LinkedIn now does have like the follow capability, and so it has a directed graph of some kind. And sorry, I just dropped the term right there. That's one of the two terms that I wanted to introduce, the definition of an undirected versus a directed graph. A directed graph, as its name implies, has directionality associated with the edges, whereas an undirected graph does not. And the easiest way to think about it is whether you have an arrowhead on the line. So literally, if I do that, that is an example of a directed edge. But if I do this, oopsies, whoa, what is that? Trippy. Right, so if I do two lines, two nodes, and a line without any arrowheads, that is a data model that is undirected. All right, people okay with that? Hopefully the social network example serves as an anchoring example here. So we have all that blah thing. Also, one other thing that, well, actually, let's think a little bit about some of the nuances between directed and undirected. If I wanted to turn LinkedIn's connect graph, not the follow graph, but the connect graph, I want to take that from a undirected graph to become a directed graph. What would be the change I need to make in the definition of an edge? In the back. What would imply the directionality?
So I would think that it would be someone communicating, sending a message to another person, whereas
Yeah.
back and forth communication would be bidirectional.
Right, exactly. And so actually, if we wanted to, I like that point about the person who initiates the request, right? The one who communicates outwards. That is the one who we could then model the connection graph on LinkedIn by not merely are you two connected, but who actually initiated the connection and who was the one who had to accept the connection, right? And in that case, we would turn it into a directional graph. So you can see the definition of an edge really matters, because if we were to try to understand the dynamics of network connection on LinkedIn, and the key question that was involved there was like, do something along the lines of, are there special properties of the people who initiate lots of connections, but yet our data model doesn't include the directionality? We cannot answer that question, right? We need to have the directionality of an edge in order to ask questions about the initiator of that connection, right? And the definition of the directed edge would have to be A initiated a connection request to B, right? Not the other way around, okay? So hopefully that really hammers home why the definition of an edge is so important. Cool. All right, final little point. I just wanted to, why I'm harping so much on graphs. Why I'm harping so much on the definition of an edge. The nodes are boring. They're your tabular data, they're boring. The part that really defines the interestingness of a graph is the edges. From the edges, you get all these fancy algorithms, ways of solving problems. When I was in grad school, one of my committee members was hosting a seminar at the Harvard School of Public Health, and John Quackenbush, who's also a faculty member there, was speaking. And I don't remember his talk. I will admit, it's been 10 years. I don't remember his talk, but it was a talk on network science. And there was one quote that really stood out. The heart of a graph lies in its edges, not in its nodes. As soon as I heard it, I wrote it down and I put it inside the tutorial because I knew I wanted to remember this and share this with everyone. The heart of a graph lies in its edges, not in its nodes. Without edges, those nodes are merely rows in a table. With edges, the interestingness comes out, all right? Cool. Any questions on this? Any thoughts?
I think the talk was about using networks for phenotypic analysis.
Using networks for what, sorry?
For phenotype analysis.
Possibly.
I've heard the same talk.
You've heard the same talk from John Quackenbush. Oh, wow. Okay, small world, small world. Okay, that probably was the one. All right, thanks for jogging the memory. Okay, so if there are any other thoughts, because if there are none, we're going to move on to the next notebook and get some coding going. Alrighty. All right, I think people are excited to go and code, so let's do that. So I'm going to close this window. I'm going to close the Marimo server, Control-C-Y, and then let's do NetworkX intro. So if you could open that up, UVX, Marimo, edit, -- sandbox, 02, NetworkX intro.py. Cool. I'm going to run a few cells. I just hit play, actually. Okay, cool. All right, so I am going to first give everybody a quick introduction to the NetworkX API, since that's what we're here to learn about. That this will then, because the NetworkX API is what will allow you to manipulate graphs in computer memory and also give you a more concrete language for talking about graph theory ideas. I do notice, like within the stats and math world, it's a little hard sometimes to communicate with other folks who may not have the exact same language, but if we have an API reference and we do nx.someAPI-name, then that's always extremely precise. So I really love programming for that reason. Cool. Within this notebook, we're gonna explore, or we're gonna use as an anchoring data set, a social network of 7th graders. The nodes, if you are curious to read a little bit more about what's going on here, there's this paragraph that is in this section. We will work with social network 7th graders. Here, what the students are the nodes. The edges are very precisely defined. The edges are how often these 7th graders indicated another 7th grader was their favorite out of 3 questions, right? And you're allowed to have multiple favorites, right? Like these are kids, so be it. If you're interested in where the data came from, there's this link over here that you can click on, the Connect Graph Data Repository. All credit to them for archiving for this. Cool. So NetworkX, it was designed historically as a Python reflection of the underlying math, and the way that it's stored is in the way that graph data are stored are in a dictionary-like fashion. You put them under a graph object like this, and so the way that you'd usually instantiate a graph would be g is equal to nx.graph over there, and then that would then allow you to create an empty graph in memory from which you can add nodes and add edges. You don't have to call it g. You can call it absolutely any variable name that you want, but there are attributes that are present on the graph. So g.nodes allows you to access the nodes that are present, and you'll notice the square selector syntax, and that selector syntax implies that implies a dictionary-like accessing of information. Edges are also accessed in a dictionary-like fashion, but it's a little bit modified for the syntax. You do g.edges node 1 and node 2, and that defines how you can access edge data from node and edge data inside here. So let's make this concrete, right? We're going to load up the data set down here. I have a custom package. I have absolutely no recollection why I keep calling this like CF as the abbreviation, but you will see this CF.whatever all throughout the notebook. So go ahead and load that up. I saw a question.
Yeah, no, I guess I'm having an issue installing maps. Is that like a...
Yes, that's the custom package. And let me just double check the notebook itself, not the dependencies, the packages.
It's going to, I guess, is that your own...
Yep, it's a custom package, and where I've put it is I put it up on my personal like my own PyPI index, which I maintain for myself. So are other people encountering the same issues accessing it?
I find that it works if I CD to the main network analysis being simple directory.
Oh, so that's how you're doing it. Okay, yeah, that is a little bit surprising because I thought I made sure. Let me just quickly do a quick detour to make sure that this is defined correctly. If folks have this inside here, UV index, tool.uv index, and UV sources, then this should actually be pulling in the info for you. But if that's not happening, company laptops. Okay, all right. I see. That might be the issue. Okay. That was a little bit unexpected. Should have anticipated this. Didn't anticipate this during the rehearsals, but now I know. Cool. Let me think here. Let me just check.
Download the wheel and then use a local link to it instead.
Possibly. That is going to induce a bit of trouble. How many people are having trouble with the NAMS package? Can I get a raise of hands? Okay. For now, are you okay pair coding with your neighbor? I will fix the issue later after the tutorial. All new experiments will incur some kind of problem like this, so I'm perfectly expecting this. I will fix the issues by actually publishing the NAMS package onto PyPI rather than doing this fancy thingamajig that I'm doing with my own PyPI server. So that will be the fix that I'll commit to. For everyone else, so if you're having trouble with the NAMS package, maybe for the time being, please go ahead and look through for the time being, use pair code, and I will find a way to get this up on either PyPI or during one of the breaks, I'll figure out how to do editable installs. You can install it from Git source as well. Like it's literally the same repo for the tutorial. All right, so that will be the way to install it. So really appreciate the patience. Thanks for flagging the issue as well. Okay, cool. For those of you who do have access, please graciously share your laptops or pair code with folks who don't. Hopefully that can help smooth over some of the problems here. Okay, so what we've done is I've done, G equals cf.load 7th grader network. There is a graph object over here. And if we scroll down just a little bit more, if I check the type of G, I'll just run it one more time, you'll notice that it is a NetworkX digraph. This is a directed graph, not a graph, which is an undirected graph. And so if I were to check the type of an undirected graph, it would be this guy over here, right? NetworkX .classes.graph.G graph versus what we have for our data, which is a networkx.classes.digraph.die, capital D, capital G, digraph, right? So far, so good? Okay. Now, we can actually query for node information, and the way that you query for node information is by doing this. I'm actually going to break this down a little bit more for everyone. So you do g.nodes first, and you'll notice what this returns is a node view of all the nodes that are present. Notice that here, the nodes are actually all just integers. They're modeled as integers. We're not putting any names. There's no personally identifiable information there. And so that's all it is. You might think, oh, I got a node view. Can I select the first 5? That actually doesn't work. And that's because the node set is a set. So there's no notion of ordering within a set. It's just a collection of stuff. So you can't go 0 to 5 and get the 0th to 4th element inside there. And that's why we have this thing where we cast g.nodes into a list constructor. And what that does is then gives me a list of all of the elements. And if you're in Marimo and you're looking at this for the first time, Marimo actually has dynamic views for, tree views, for basic data structures in Python. So item 0 is node 1, item 1 is node 2, item 2 is node 3, item 3 is node 4, etc., etc., etc. All right, so this allows you to like browse through the item list inside here. I can collapse that and that'll be fine. And then from here, I might do selector out 0 to 5, and that will change the number of items that are being displayed. And now I only have items 0 to 4, which correspond to nodes 1 to 5. So then the students are one indexed, just to make sure this really clear for everybody. The students are one indexed, and whereas the rest of the ordering on the left-hand side is 0 indexed, all right? So just don't be confused by that. Okay, cool. And so I'm gonna reinstate this guy over here. Question?
My printout is just printing the numbers, it's not printing the np.int.
That should be okay. I wouldn't worry too much about that. Ooh, we've got feedback. All right, no worries. We'll work through that. One more. Yes? Yes, that's right. So within this data set, student number 1, student number 2, student number 3. Any other questions on the data? Okay, so you can actually do len of g.nodes, right? So if we recap, g.nodes is a node view object. It is set-like. So you can actually call the length of the set. You can know how many elements are present inside there, and there should be 29 students that are represented inside this graph. If we were to also pass in g.nodes data equals true, so if you would like to go ahead and type along with me, g.nodes, and you do data equals true, what we're going to get is something that's slightly different, right? So now what we have, I'm actually going to cast this in a list in front of everybody. What we have is this following tree structured thing, right? We have 29 items, index 0 all the way to 28. Student number 1 through student number 29, I am going to use the student ID, not the Python index. Student 1 to student 29. And that is represented by each of the tuple or list elements that are here. It's actually tuples, they're not lists, even though they're shown like lists here. So each of these items that are returned are actually a two-tuple. The first element is the student ID over here, or the node ID, so to speak. And then the second element is a metadata dictionary. So in this case, like I've mentioned in the paragraph above, what I've done is to make this graph, although all of the students here the data were originally from an all-boys school, I've actually changed the data a little bit such that we have some interestingness by doing this from a mixed school rather than a all-boys school. And so we've got some students who are male. Let's see if we can find, there's some students that are female, right? So like just injecting some interestingness here, all right? Any questions on that? So when you do data equals true on g.nodes, you're actually also you're not only returning the node as it's identified in the graph, but you're also returning the metadata dictionary that's associated with it. Nodes, because they are part of a node set, they have to be hashable. So strings are okay as a node, but lists are not acceptable. On the other hand, you can have tuples. If you really need an iterable of diverse elements, you can put a tuple as a node. And tuples are hashable because they are not mutable, and therefore you can put them, you can use them as nodes as well. Okay, all good? Cool stuff. I'm gonna collapse this all down. If you want to select out an individual node, like g.nodes of student number 1, you'll get back the metadata dictionary itself for the node. So if you wanted to access student 28 was a female student, right? All good so far? Okay, cool.
Why can you access it by index but then not slice? Like
That's a design choice because this is dictionary-like. So 28 is an integer that is hashable, so I can access the metadata dictionary for that in a dictionary-like fashion, but I can't slice because there's no notion of order in dictionary keys.
But it doesn't, I guess, because it's hashing, it doesn't guarantee you that one has some sort of natural ordering on it.
That's correct. That's correct. I think if I remember correctly, recently Python dictionaries accidentally got automatic ordering, but it was never intended as a design choice.
Can you go back up to your last command that you used to explore the anatomy?
Yes. So scrolling back up to here, g.nodes, and I can sorry, actually, might have acted a little too fast. List of g.nodes with data equals true. And if you want that, you would basically just take out the print from here. Okay? Cool. Now, you can loop over a set, just like you can loop over g.nodes. And in fact, you can do the tuple unpacking straight away. For n comma d in g.nodes with data equals true, you would do for n, yeah, and that basically looks like how we would loop over a dictionary, right? So like this code over here for n, d, etc. N is therefore the node, d is the metadata dictionary, and it looks just like for kv in dictionary.items, right? And so then this now leads us to our first exercise, which is I would like you to count the number of males and females that are represented on the graph. So please take 5 minutes, do this exercise, and flash a quick thumbs up if you are done so that I know that you're finished with the exercise. And feel free to pair code as well. So don't feel like you have to do this on your own. That is surprising. Thank you for finding that. One moment. In NetworkX intro.py?
And in Viz. Check
And in Viz? No, it's 0.0 for me, but okay. If that, you want to put your laptop here?
Yeah.
Yeah, go for it.
Let's check the latest. So if I go to
Oh, wow. How did that happen?
So I just removed the version number and then it backfilled the version it found.
Oh,
So
okay.
if that's a good thing or what, but
Maybe. Okay. Okay. All right. What's your name? Sorry. Jordan. Okay. We are on 02 NetworkX intro.py right now. So if and actually Jordan, one of our tutorial participants, noted that if you have issues that are not, say, TLS related, but happen to have like NAMS double equals 0.9.2, not sure how that happened. Might have been a clerical error on my side because 0 and 9 are right next to each other. If that is what happened, then feel free to change the 0.9.2 to 0.0.2. You probably still do need to change the UV index, make sure the UV index is set correctly to make that work. And at the same time, I'm asking for AI assistance on how to change this to make sure that we're pulling from Git repository source as well. there. That's okay. Yeah. Okay. All right. I think I can confirm this change will probably. So let me try this. We take out UV sources, UV index and UV sources. That is suboptimal. Okay, cool. All right, I'm going to take that out. Yeah, that's not the option that I want. All right, cool. Okay, it's been a few minutes. How have people finished this exercise? What you should get back as a data structure, if you want this to be compatible with the test that is below, is you should get back a dictionary or a counter object in which your key is the gender of the student and the value is the number that you've counted over there. The way that I would have done it is basically for n comma d in g.nodes data equals true. We would do, so mf counts equals counter, and we do from collections import counter, and then we just basically do mf counts if d mf counts d gender plus equals 1, and that should be the tricks. That should do the trick. Yeah, that did the trick. There we go. So then that will then allow me to pass these tests below. Just flashing it up for everybody. That is my solution over there. Hopefully you got something analogous. You're just using a dictionary of some kind, and that should do the trick. All right. Everybody okay with this? Thumbs up? Okay, I see thumbs up coming up. Let's move on to the next one. You can also query edge information. So same concepts, g.edges on its own, and you'll notice that this is a two tuple, right? So just to really hammer home the point, I can do list of g.edges, and so then now I have, how many edges do I have here? I have 376 edges that are represented on the graph, and for each edge, I'm representing it by a two tuple, which is the two integers, right, between which I have a relationship between those two students, or an edge between those two students. And so then, again, I can also call on len of g.edges, and I can also query for metadata that looks like this. So I can do list of g.edges, data equals true. And you'll notice now, instead of a two tuple, I have a three tuple. And the elements per edge, I have a three tuple, and the first element is the first two elements are the nodes that are involved in that edge, and the third element is the metadata dictionary. And in this case, the metadata dictionary is literally just how many counting how many times one student rated the other as their favorite, all right? So this data should be correct. If the edge does not exist, if an edge does not exist between two students, you should get a key error, and it'll look like this. So this actually is a legit error that should show up in your notebook. G.edges of 15 and 16, though that edge does not exist. On the other hand, I think 1 and 2 does exist. And if 1 and 2 do exist, then you'll get if the edge between two nodes exists, then in this case you'll get the metadata dictionary, which is the count of the number of times they rated each other as their favorite. Cool. Just like nodes and looping over nodes, you can loop over edges like this. And so that launches us into the next exercise, which I'd like you to try, which is to verify that this is doing a data integrity check. I want you to verify that the maximum times any student rated another student as their favorite is actually 3 times and no more than that. So figure out your solution to that. problem. I'm going to type it live on my side as well. All right, how are people doing with this exercise? Thumbs up if you're done. I'll give folks a few more minutes. I have my answer flashed up if you're curious to see what it looks like. I may have had a typographical error in the comment here. It's not assing, but a sign. Apologies for that slip. Okay, how are people doing? All okay? Thumbs up? Okay, still see some folks working through it. All right, while people walk through it, I'm gonna quickly step through the answer that I have. The idea here is I wanna write a function that returns an integer, and that integer is nothing more than the maximum value of the counts metadata that are present on each edge. And so what I would do is in my case, I just collect together a list of counts and loop over each of the edges. So for n1, 2, n2, n1, n2, d, I could actually do it this way for underscore, underscore, D, and that's perfectly legit. Underscore is like a placeholder variable for stuff you don't want assigned in Python. And then you do D in g.edges data equals true. And then you can do counts.append D of count, right? And because that the count key is what we want to access from the metadata dictionary. And what I would want to then do is grab the largest value from counts, this list counts, and return that. And then I can assign it to the variable max count equals edge metadata answer of G. All right, so that's the answer here. If you're curious, I think we have solution answers over here. So notice on the right-hand side, there's these like horizontal bars on this side of the screen. So I'm just gonna like circle it if I can, right over here. If you mouse over, that gives you an index, like a table of contents, TOC, for the notebook. You can actually click down to the solution answers and take a peek on any exercise that is present inside this notebook. It's not too, shouldn't be too difficult to hit that. And as you know, if you're genuinely stuck, feel free to just look at the answers. There's like Montessori style education, we give ourselves as many chances to master the thing that we want to learn. All right, so no pressure to get it right the first time around. Okay, and if you implemented this correctly, this testing cell should execute fine and should return no errors, no assertion errors, right? If max count was like 2, we would have an assertion error, but max count is not 2, so we're good. Question in the back. Yeah. Oh, that's a good question. Okay, so this is maybe one of the things about Marimo notebooks that are making this a little bit more challenging. In the rehearsal that I did in Boston, people also asked the same question. I think the way to look at it is as such. You'll notice that, at least on my Marimo UI, there's a very subtle color difference for the numbers on the left and the data that's on the right. So the numbers on the left, those are Python index. They aren't the data itself. All right? The real data are on the right-hand side over here that I'm highlighting, right? And so I don't know if I can do this like any more precisely than trying this guy. So if I were to draw this line over here, do you see that? That's the data, and this is nothing more than the index. So we don't care about the index. This, on the right-hand side, the first 2 elements of this list, or this tuple, sorry, they are the students' indexes. So index 1 and index 2 have an edge between them. And then down over here, that is the metadata dictionary. That is the 3rd element of this 3 tuple, right? That is correct. That is correct. That is saying student 1 liked student 2 only one time. And if we were to scroll down and try to look for a counterexample to this, over here we would say student 1 said to student 6, rated student 6 as their favorite 3 times. Okay, and then follow-up question.
Yeah, and so this is a directional graph, correct?
That is correct.
So this is saying that
This is directional.
the direction is from student 1 to student 5 or to student 2.
That's correct. So this is the direction is from student 1 to student 5. If there was an unrequited friendship, then you would not have the opposite direction edge, say 5 to 1 or 6 to 1. And so in this tuple over here, the order matters for directed graphs. The order does not matter for undirected graphs. All right? Okay, so hopefully that clarified how to read the Marimo tree data structure for everyone as well. I think I saw another question in the back. Was there one? Okay, yes?
So if it's bidirectional, maybe you'll get to this. If it's bidirectional, would it differ from that then?
That's correct. So if there were a bidirectional graph, actually, let me try to find that inside here. So if I were to do g.edges 1, 6, that does, wait, where are you? Right there. 1, 6 exists. Does 6, 1 exist? 6, 1 also exists. So I executed the cell. 1, 5, does that exist? That exists. It has 2. 5, 1 is different. All right, I'm not sure if this is showing up clearly, so I'm going to zoom in a little bit even more. 1, 5, count is only 2. 5, 1, count is 3. So something must have happened somewhere between these 7th graders, right? Does that make sense? Does that make clear, like the storage of directional data within, yeah? Okay, within a directed graph. Yes, question? So the question is, do they support what graphs again? Chain graphs. I think, so the way that, so NetworkX itself, if you define a digraph, you are required to specify bidirectional edges if you want to model the equivalent of an undirected edge. So that would be, so the direct answer is no. I don't think it's possible to do chain graphs as you've defined, but there is, yes, a way to do it, to use the digraph data model to then try to model such a graph. Okay, cool. Thanks for the question. That's correct. That's correct. So the question is, isn't this just a bunch of like one directional edges, right? Like, and the answer is correct. If you want to have, that's the core of a digraph. Every edge has a direction. And so if you want to model bidirectional relationships as if they were undirected, you'd actually have to find a way in the directed graph to automatically generate the complementary edge in the opposite direction to turn it into the equivalent of an undirected. Okay, cool, great questions, I love that. Cool, let's move on. If we scroll down, okay, I need to zoom out a little bit so I can orient myself. Cool, so we've learned how to query a graph for information. This is kind of literally the syntax that you would use. You're accessing node dictionaries. What we're going to do next is we're going to learn how to add nodes and add edges. If you scroll down a little bit, there's the add node and add edge API. I want to walk through this a little bit because I think there's some cool magic that's going on. So if you want to add a node, what you do is you do g.addNode and you pass the node in to the graph. Then what happens at the end on the other side of the node, like within the addNode API, is you can add in certain node metadata through keyword arguments, KWArgs, right? And this is a magical way of adding in dictionary information. So you can actually do node data, like some key equals some value, and that will show up in the key value dictionary. And then you can do some data, again, some node data 2 is equal to some other value that will again show up as a different key in the metadata dictionary. So in the exercise below, literally you could do g.addNode, some node ID, and then count equals 2, and that will work. Same goes for adding edges. You can add an edge between two nodes. So you would pass the two nodes over here, node 1, node 2, as the first two arguments, positional arguments, and then you'd put as keyword arguments your complete set of metadata that you would like inside there. All right? So far, so good? So with that information, I think you have enough information to go and add students onto the graph according to the specification on this paragraph. There were 2 students that were left out of the network, number 30 and number 31, one male, one female. They're a pair. They just love hanging out with one another, but they also love hanging out with individual 7. And that means that what that implies for the data are that you would put count equals 3 for all of their edges. So in both directions per pair. So I'd like you to add this information onto the graph. So that should be a 5-minute-ish exercise. And I'll code along as well. Question?
In the answer that you just wrote out, would it count be equal to 1 for each edge if we're defining it 6 times?
Oh, that relates to the definition of this data model. The answer is no. So the question is, wouldn't we put count equals 1 if we were defining this 6 times, right? The way that the data were collected are that the students were asked on 3 separate occasions, who are your favorite friends? And you're allowed to rate more than one friend as your favorite friend. So count equals 3 implies that on 3 separate occasions, 30 rated 31 as their favorite and 31 rated 30 as their favorite. But then also 31 rated 7 as one of their favorites as well, right? Does that kind of make sense?
I think so.
Yeah.
So it's like a range of 1 to 3.
Yes. So your values on the edge can be 1, 2, or 3. That's correct.
Does this kind of allude to edge weight?
Yes, it does. It does link to edge weight. That is correct. Question. Actually, I'd like to get your voices on the YouTube recording. So, Eric, could we have the mic passed around, please, for questions? Yeah, so question up front. Make sure it's turned on.
Is there any best practices for when you add the nodes? I mean, right now we're just doing numbers, but like having a class or an object, is there any like anti-patterns or best practices for setting up these nodes?
Yeah, good question. So I don't think there are, with NetworkX, the only technical requirement is that your whatever is a node, whatever you pass in as a node, needs to be hashable. So I think you need to ensure that you have a hash function, hash dunder method, applied if you have objects that are passed in. Perhaps maybe one thing to keep in mind is that usually we don't tend to have a million Python objects defined in our program code. So it ends up being a lot easier to define. So like, if you imagine if you were to pass in objects, you'd have had to create and instantiate them first. But then you kind of end up needing to then, if you need to access any arbitrary node, then you need to have the object reference available and handy. You might have a helper function that lets you do that, or you might have to end up defining all million objects in memory, whichever. But it just ends up being like maybe easier to define strings as your nodes, and having a naming convention for your strings which then makes it, you can then keep the actual object as the metadata itself. And that makes it maybe a little bit more human-friendly to program and interact with the graph object. Thanks for the question. Anything else? Cool. So if, I'm just going to quickly run through my answer over here. I create a copy of the graph because I'm not interested in mutating the graph, original graph, and I think that's generally a good idea to do. You can do g.addNode of 30, g.addNode of 31. Those were the two that I added. We added those two metadata fields there as well. Then I added the edges pair by pair, so added 30 and 31, the pair of edges, 7 and 30, and 31 and 7, and then I return the graph over here, and so that would be G1 over here. And then what I do down below is I'm just testing the graph integrity, so I wrote a little software test for that, and this does not error, and so we know all tests pass, which means we created the graph correctly. Question in the back. Eric, can we get the mic there, please?
So I understand how we're creating this and appending. If I had a tabular data set, right, I could do a lambda apply function. Is there a better way to just do this in mass?
Yeah, so if you had tabular data already present, you could do a for loop over your, let's say you had an edged list that was stored as a pandas data frame, and one column was your nodes. Node list. Let's do the node list and then do the edge list. So you had the node list in a pandas data frame. You could, in theory, for example, do, you could add nodes by looping over the pandas data frame and then taking one of the column values as the node identifier itself. You add node on that column value, and the rest of the columns turn into metadata. If I remember correctly, Eric, I think I might need some help remembering, but I think there is a NetworkX API for loading node lists and edge lists from pandas data frames. Yes, that's right, in NetworkX as well. So that is also doable. And it's in the API. Also in the notebook IO, input-output, which we should cover by today, there's an example of doing that en masse. Great question. Thanks a lot. All right. Anything else? Yes, question up front. One moment.
Is it possible to, like, you query an edge by doing 31,7? Can you just do g.edges 31,7 count equals 3? And if it doesn't exist, it would just place it in there? Or do you always have to use the add edge, add node API?
Yes, the answer is the latter. Yes, you have to use the add edge API. And in this case, I don't think you can add edges by doing g.edges 30,7 because that would end up doing an accession, like accessing of, we would attempt to access that edge. And so that would first throw a key error, right? Like that edge does not exist, right? So the order of operations as designed in NetworkX are such that if you try to do that, you wouldn't do an assignment. You would do an accessing of the variable underneath the hood, and if it doesn't exist, then we throw an error. Cool, thanks a lot. All right, any more questions? Great discussion, I love that. If not, I'm gonna move on. There are some coding patterns that I've come to realize are pretty handy. If you know how to do list comprehensions, you can condense a lot of the for loops into list comprehensions as follows, like this guy over here. And you can do the same thing with edges by doing also list comprehensions. If you are doing a directed graph, I think some of the naming conventions for your loop variables can really help. So you can do source and sink, or SC, SK, or SRC, SNK, whatever floats your boat, but just name them not N1, N2, but something that implies source and sink if you're doing a directed graph and you're looping over the edges that are present. Cool. If you want to, we're going to take a quick break, bio break, 10 minutes. If you want to nerd out, you can do the exercise down below, which is the unrequited friendships exercise, which is to ask, which students said they like the other, but they didn't have their other friend didn't say they like them, right? Like And there are multiple ways you can solve this. The one that I think we're looking for is like, is there an edge in one direction but no edge in the other direction? We're not looking for balanced edges in that sense, okay? Okie dokes, it's 9:40. Let's get back to the next notebook. Just out of curiosity, how many did the unrequited friendships exercise? We've got some budding sociologists, just joking, data science sociologists in the crowd. Cool, let's move on to the next exercise. Actually, just out of curiosity then, how many unrequited friendships were there? 124. Okay, cool. If there's consensus, then that's probably correct. Yeah, 124. Sorry, I put it inside the answers there. Cool. So let us close the notebook and let's go to the visualization notebook. So we're going to do UVX Marimo edit sandbox 03viz.py. And bingo, we have it here. All right, so just now we had an introduction to how to, in how to like manipulate NetworkX graphs. We'll take a short little break from hardcore programming for a little bit. This notebook is a little bit more of a walkthrough and discussion about how you visualize graphs, because if you can imagine, if you grab in a network, the most common visualization that you might see is a hairball, right? Just lines and circles with the lines drawn all over the place in straight lines or curved lines or whatever, but it'll look like a tangled mess, right? And so it's convenient, right? Like to draw it this way, there's nothing wrong with that. And if you run this cell down over here, nx.draw of g in plt.show, you'll see it looks like the student network that we just were manipulating looks something like that, right? Doesn't look that pretty, I'd say, right? But yeah, you'll notice that, so the type of, maybe to not be so facetious, this type of network diagram I think is called a force-directed network diagram, and it's the default that most people will pull towards. The idea here is that like if you've got edges between nodes naturally want to repel each other, but edges tend to want to pull nodes together. So if you have tight clusters of nodes, this becomes an easy way of identifying clusters of them. And so maybe it's not as uninformative as I would sell you on, but like there is some kind of information that you can see, like this node out here, for example, is not tight in a tight network with many of the other nodes. And you know, a teacher who is savvy sociologically would look at the graph and start to go, which students might I want to put more attention onto because they're feeling a little isolated, right? But that in and of itself doesn't feel like a very informative graph visualization. So I wanted to walk through a few others that are out here, right? Oh, sorry, I thought there's actually a few more things. With force-directed graphs, you can actually, NetworkX itself has the ability to annotate nodes with the labels. So whatever is the hashable object that you put on as the node, it will try to do a string rendering of that guy and put that on the node itself. And so, yeah, the big downside here is that it looks like a hairball, really. Question?
So like each time I run the plt.show, the graph is slightly different.
Yes, good point. And that's because the graph layout algorithm is non-deterministic. It's got randomness. If you think about it, we are not prioritizing the placement of nodes anywhere. We're just saying initialize and then let the graph sort of repel and attract, let the nodes repel and attract in some, according to the force field defined by them. And then it just settles into its own energy minima, basically. And that's exactly what's happening over here. So it's non-deterministic because we don't have a rule by which we place the nodes. And that's a really great segue. I promise I did not plant your question. That's a really great segue into how we do rational graph visualization. So this looks like a hairball. I don't think that's necessarily the nicest. So there are different ways. And the first one that I want, there are better ways, there are different ways. And the first one that I want to showcase to everyone is what we would call a matrix plot, all right? And this has direct connections to how graphs can be represented in linear algebra form. So if you are savvy with math, this should become pretty familiar for you. Take a look at that. That is one visual representation of the graph. And in this visual representation, what we have are the nodes ordered along the x and the y axes. So the y axis and the x axis that I'm highlighting over here, they are clones of one another. We clone the axes. We group the nodes according to their attributes. So we've placed the female nodes over here, and then the male nodes out over there. And then we fill in the matrix with a dot if there is an edge between any pair of nodes. So this dot over here indicates that this student, this particular student down here, has a connection to this student over here, right? And so literally every graph can be represented as a matrix, and you get to choose what values you put on that matrix. I could choose, for example, to highlight by the weight or the count the count metadata that's on the graph, or I could just convert it into binary 1, 0. Is there an edge or no edge, right? So that's the first one. What can you tell immediately about this graph? What comes to mind? There's no diagonal. That is a very, very good observation. So the diagonal is empty, right? Because we don't have narcissists who are rating themselves as their favorite, right? Like that's a great thing for this generation, because I know there was a generation out in Europe that was raised to be narcissists, fearless, and etc. in the 1940s, and that was not a good time for Europe, right? So what else is there? What else do you notice? Ariana.
It's mostly symmetrical, but not exactly, because some students are friends in only one direction.
Yes, it is mostly symmetrical, but is not guaranteed to be symmetrical, and that is a property of a directed graph. Directed graphs are not guaranteed to be symmetrical along the diagonal. Undirected graphs, on the other hand, when you represent it as a matrix form, you're guaranteed for them to be symmetrical, all right? And so, exactly as you're saying, there are certain friendships that are not requited, so to speak, like this one down over here. This male student and that female student had one direction, but on the opposite corner up here, it is absent, right? So people got that. Cool. Those were the big salient points that I've written down here below as well. And so you might argue also that there might be some clustering happening. You know, like there's some one other salient property. Sorry, actually, is like I'm not sure what's going on with these. These two students over here, right? If you look at this column, what's up over there, right? Like, why is it so full? Do they really have no preference with their friends, or is there something else going on there, right? So like that's another salient feature. Whereas like, what's up with this student over here? Like this poor soul, like got only one dot on the vertical, right? Like that feels a little bit, not sure what's going on there. So some students might be lonely and isolated or something like that. So this is an immediate visualization that can tell us that. Okay, so that is one, sorry, I'm coming back here. That is one visualization. I want you to remember, prioritize the placement of the nodes, right? So the nodes placement, if you prioritize the placement of the nodes, then your edges become easier to draw, and it becomes a lot easier to reason about the relationships. So let's see that in action with another alternate visualization, which is what we would call the arc plot. And the way that we draw an arc plot is as follows. I'm going to just visualize this out here. It's almost like the matrix plot, but the key difference here is that we are ordering nodes along the x-axis and then drawing arcs between nodes if they have a connection, all right? And this allows us to then quickly visualize, hey, which are the nodes that are, say, this lets us visualize very quickly what are the intra and intergroup connections. But there's actually an even better visualization for that I'll show you down below as well. If you imagine the arc plot as being like I order my nodes along the x-axis and then I take the two ends of the arc, like the horizontal axis, and join them together, then what we get is the Circos plot. And the Circos plot looks something like this guy over here. Super beautiful, right? Especially if you had, yeah, it's super beautiful. It took me a long time back in 2016 to figure out how to draw arcs like this in Matplotlib because I was not very familiar with the API. But once I saw it, it was just wow. It was a wow moment for me. And it allows me to visualize, again, the connections within and between groups. So I think there's a question over here. Eric, can we get the mic, please?
For both this and the arc plot, and I guess also the matrix plot, what's determining the order of the individual nodes?
Yeah, great question. So the way that I order right now is arbitrary, but the way I'm grouping is not. So I could apply a default ordering by according to index, and actually we'll see this in a later notebook where we talk about the spread of infectious diseases. We do an explicit ordering of the nodes that show up, and that induces a different Circos plot as well. I missed the second question. What's determining the order? And
I think that was just
that was it?
question.
Okay.
Yeah, yeah.
All right, sorry about that. Thanks a lot. That's a good question. Thank you.
So in a pedestrian example, like let's say a transportation network, what is an intuitive way of ordering and graphing the topology in one of these abstract ways?
Yeah.
And you are going to go over this in your epidemiological example, but what is the thinking behind the best kind of spatial indexing to use in the ordering?
Yes, good question. So the best spatial indexing is the one that fits the problem the best. And so if you have transportation networks, I would actually not recommend doing any of these abstract ones. You should place your nodes according to latitude and longitude. That is the one that makes the absolute most sense. And there's an example of that in one of the later notebooks as well. Cool. Another question.
Hey, this is great. Thank you. These are beautiful, but I'm wondering, well, what do I learn from this?
A good question.
So I guess I have two kind of sub questions. One, how do you think about sort of the grouping and ordering of the content so that you can see maybe some natural gaps?
Yeah.
And then secondly, and this is maybe an aside, are there other libraries that enable kind of maybe interactive filtering or something so you can sort of see what changes? Because there's so much information on this one diagram as an example.
Yeah, that's a great question. So to respond maybe to like how do we know where, I think the first question really was like, how do we know by what should we group or should we order, right? And that is a problem specific thing, right? You can think of it this way. If you were looking at a node table, how would you want to do your group by? That would be then the property by which you would create the graph visualization and group by a certain node category or node label that way. And then if you were again looking at the node table, for the problem that you had at hand, if you weren't making a visualization, you were just like analyzing the table itself, is there a natural ordering? That would be how you would sort the nodes. So grouping and sorting, those idioms that apply to graph visualization really have a lot of parallels to how you would do your analysis in tabular form. And so if you found a way to naturally group by or order by in your, group or order by, then you can apply that to the graph visualization itself. I think I missed the second part. Interactivity, yes. So interactivity is a great one. To the best of my knowledge, there are no good tools for interactive rational graph visualization. I've attempted multiple times to find the time outside of work to implement this in NXViz and have never found enough mental energy to make that happen, but it is a dream. I think one thing that could help would be, Altair style declaration of like marks and I forgot what the exact syntax is, but Altair has a very declarative style. And if we have naturally categorical things, you can group by them. If you have naturally numerical things or ordinal things, you can sort by them. And I think that's maybe one way that I would go and implement that inside like an interactive view where we're dynamically changing the ordering of the nodes and then just redrawing the edges according to whatever properties we're grouping and ordering by. But the most important lesson from this notebook really is you should know how to group and sort your nodes. That is the most important thing. In the absence of interactive vizzes, from a good data viz practice standpoint, if you're able to create small multiples, that is to say multiple panels, circles, this is a circos plot. And if you did grouping a different way, you would basically have a circos panel, right? Where you could like group by different properties and then study your data that way. And that would be the way to do it in the absence of actual interactivity. And I think I saw one more question on this side. Was there?
Well, I would also add that grouping by communities is a great natural way to do these plots.
Yes.
And you can
yes.
also like sort by some metrics you compute
yes.
on the graphs.
Yes,
but
that's right.
Probably later.
I guess one question I had is, I always found circus plots really hard to interpret because it takes quite a bit of effort to understand the relationship between the nodes and the edges
Yes.
in a circus plot. And I spent a bit of time thinking of like data viz accessibility last year.
Yeah.
And this plot is one of those which is super hard to,
It is.
I guess, like get across the barrier.
Yeah.
It's so difficult to write like a alt text for a circus plot.
Right.
And I guess I was just wondering if you had any suggestions for any tools that were already in place or like any frameworks that have implemented accessibility for circus plots.
That I'm not very well educated on. You probably have more info than I do on that. That said, when you mentioned alt text, I did think about how I would describe this plot to a person who was not able to see the plot clearly. And one of the ways to do it is to describe the placement of the nodes. So you could say like, I have nodes that represent people. They are ordered in counterclockwise format from 3 p.m. They're ordered counterclockwise starting from the 3 p.m. position. There are curved lines that are, continue describing the node grouping. Those nodes are grouped by the gender of the people. They are not ordered in any particular way. And there are edge lines, curved lines that are drawn between them. And naturally, the curved lines are hard to describe, I think. So that makes it a little bit more challenging. Hopefully that addressed it. I think there was one more. Oh, over there, yes.
So it seems a bit limited by the data that
Yes.
all of these edges have the same strength.
That's right.
And so you can't do anything like pruning or thresholding or anything that could cluster certain relationships or
Right.
make groups more apparent.
Right. So what we would do, like what I might do is I might do a circos panel that shows the count equals 1 edges, count equals 2 edges, and count equals 3 edges, and use that for like comparison of what the graph looks like. So that would be possibly one way to get around that. But yes, absolutely. The limitation of the viz as it stands right now is that the edge weights are not factored in, right? And so that could be an improvement here. Was there one more question or point here? Okay.
Just to follow up on this, with respect to the grouping, if you were to compute some of these things, clustering or maybe the differences and things like that, where would you add that information to the nodes or something? Because I'm thinking, like on your prior matrix diagram, you might say put all of the fully connected people on the left of their whatever group they're in so you could see the outliers. And
Yeah.
right now they're sort of mixed in.
Yeah, that's right. So you might do a clique identification and then add the clique the clique index onto the node as a metadata and then plot and visualize that. So that would be the way that I would do it. You'd really want to calculate properties of the node and then add that property, calculated property, back onto the node as metadata, and now it's available for, say, NXViz to go and visualize. That's a good question. That's a great question. And I think I saw one more on this side over here.
I was thinking about adding color to the lines connecting the nodes.
Yes.
So for instance, you could have a color for the nodes that go to females, and a color for the ones that go male to male, and then a color for the ones that combine.
Male to female and male to male, yeah, or female to female. Yeah, okay,
You could see patterns.
that could work as well. Or we could try the next visualization down below, which is the hive plot. And the hive plot is actually kind of cool because then what we do within a hive plot is we actually are explicitly plotting the intra-group, intra-group, which is over here and over here. Those are the intra-group edges. And then we have the inter-group edges this way as well, right? So those are these guys out here, right? So that would allow us to then possibly plot, visualize whether there were interesting connections that went in one particular direction or another. I'll note though, hive plots do have a limitation. You can only, within one hive plot, at most visualize 3 groups worth of connections. So you sometimes cannot visualize, if you have like 5 groups, you'd have to do 5 choose 3 number of plots in order to fully visualize the connections between all pairs of groups inside there. So that's a limitation of hive plots. Every plot, every diagram that you can think of for visualizing networks will have its trade-offs. And so really there is no ideal plot that you should go to all the time. You really have to think hard about what's the point you're trying to communicate and choose the plot that makes the most sense. So if you want to do like intra-group, if you want to really highlight intra versus inter-group communication or connection, you might choose the hive plot. If you had too many groups, but you still want to emphasize that, you would choose a hive panel where you do small multiples of different groups that are being highlighted. If you wanted to do just something visually, aesthetically pleasant, then you might choose to do like a Circos plot of some kind, etc., etc. Okay. Any more? That was a great discussion on plotting. Let's move on with the next notebook, and after the next notebook, which is going to be a little bit more intellectually demanding, we'll take another bio break. So let's close this notebook. Save, Control C, Y, Enter, and now let's go to, we're going to need to CD up one directory because we're out of the introductory notebooks now, and we're now going to CD into 02 algorithms. And we're going to do 01 hubs.py, UVX, Marimo, edit, sandbox, 01 hubs.py. Just now, Eric Welch mentioned that there may be some notebooks that have out-of-date dependencies. Marimo should actually automatically prompt you to install them. And so if you're prompted to install them, just go ahead and install those dependencies over there. Okie dokes. So let's talk a little bit about hubs, or important nodes within a graph. That's what this notebook is all about. So I think everyone in the room survived COVID. That should be true. And as a result, of COVID and perhaps other pandemics that have happened in the past, the importance of epidemiology at least should be somewhat present within our minds. I personally studied a little bit about flu transmission during grad school, and so the idea of like mapping out how flu spread globally was part of my thesis, how flu genomes spread, not how flu spread. It wasn't true epidemiology, but nonetheless, minor detail. But contact tracing is something that's really important. And What might define in an infectious disease spread situation as an important node might be someone who would be considered, say, a super spreader, right? So if we have nodes as individuals and infection paths from transmission from one individual to another, the super spreaders are the ones you want to look out for, especially if the virus doesn't kill you but really harms you, and that has a big incubation period. The super spreaders are where you might, for example, want to go to look at. And so those it might be that they were super spreaders because they were all physically in contact with, physically within the same room, and therefore the air between them put a bridge between those individuals, and that one person just was like, spread it to everybody, right? So within this notebook, we're going to use the socio-patterns data set. It is not actually a contact tracing data set. Instead, this is actually about the face-to-face behavior of people during an exhibition in 2009. And it's at the Science Gallery in Dublin. And the exhibition name is Infectious Stay Away, right? Like that's the name of, that's a bad highlight. Okay, so Infectious Stay Away. That is the name of the exhibit. What are the nodes here? Nodes are the visitors to the exhibit, and edges represent face-to-face contacts between people. So all of us here, we'd have considered to be face-to-face contacts, and unfortunately, I think I would be considered the super spreader since I'm spreading information to everybody here in that particular network. Now, in the original data, multiple edges are allowed, but for the sake of convenience, what I have done is to condense the graph such that we only represent the last contact between individuals, and just for today, we're going to pretend that that is the only contact between the individuals, even though there could have been more. So let's scroll down a little bit and load the data set into memory. And let's check the graph type, and it should be an undirected graph object, right? So people should see that in your notebooks as well. Without doing any, like when you get graph data, first thing I think that is very important to do is to know how big your graph is with respect to the node and edge set. So we have 400 nodes and 2,700 edges. One of the reasons why this is important is because you can imagine if this was a fully connected undirected graph, I should have 410 squared divided by 2-ish number of edges that are present inside the graph. But we know that, and that, what is 400 squared? 16 with 4 zeros would be 116,000? 160,000, I think, 400 squared. Well, I can't do math. 160,000. So we would have, in theory, 160,000 edges, but I only have 2,765. So really, if I were to do a graph visualization, this should be a very, very sparse graph, right? Cool. So let's, and that's important because if you want to do like certain sanity checks on your graph, you want to make sure that your sparsity is where you expect it to be. All right, so one measure of importance of a node would be how many neighbors people have. So how many neighbors do you have physically right now, right? If you count it just forward, backward, left, and right. Like this gentleman in front has one behind him. Who is it? Ariana, you're on that corner. You have 1, 2, 3, so you have 3 neighbors. And basically, it's within a graph, how many people are you connected to or how many nodes are you connected to? That is the number of neighbors that you have. And so the neighbor of a node is connected to that node by an edge. That is the definition of a neighbor. So you can actually access out the neighbors of, say, any node that you have in the graph. So node number 7, for example. These are all integer indexed nodes, so you can just pass in an integer here. So you might do g.neighbors of 7, and that gives you a dictionary iterator object. And so that doesn't really tell us who the neighbors are. However, I can still check what the, oh no, I can't check the length, but I can cast this, I think, as a list, right? And that gives me the identities of the neighbors of node number 7, which are node number 5, 6, 21, 22, etc., all the way to 51, as shown up here. And as a result of casting it as a list, I can calculate the length, whoopsies, of that. And I know that this node has 7 neighbors. Node number 7 has 7 neighbors. I can do it for another node, node 51. It has 50 neighbors, all right? Everybody okay with that so far? Cool. Oh yeah, we have that down there. So first exercise here, we'd like to find the most important nodes in this graph according to the number of neighbors it has. So I'd like you to go and discover that in this exercise. So just a few hints. You could consider using a pandas series. So if you have a dictionary that says here are the neighbors of that particular node, right? Then you could consider, or sorry, if you have a dictionary of here's my node and here's how many neighbors that I have, you can pass that into a pandas series and then you can use some pandas series methods, or you could consider using the Python sorted function, whichever you choose. So let's spend 3 minutes or so to run through this exercise. Oh, QT problem with visualizations. Eric, do you think you could help with that one? That problem sounds like a weird one. Okay, quick sanity check. Thumbs up if you're done. Okay, cool stuff. I've flashed my answers up there as well. I'll give maybe another minute or two. Don't worry if you're not done. We'll run through the answers together. Alrighty, so I'm gonna, in the interest of time, I'm gonna run through the answer briefly. I'm gonna zoom out a little bit so the formatting renders a little bit better. Within this function, rank ordered neighbors answer, I have num neighbors is initialized as an empty dictionary. Actually, just to be explicit, let's do that. Okay, so num neighbors is initialized as an empty dictionary. What I want to do is calculate for each node how many neighbors they have. So I'll loop over the nodes without data equals true, because that's unnecessary here. What I'll do is calculate the number of neighbors that are present by doing length of the list of g.neighbors of n, and then assigning that to the key n in the num neighbors dictionary. All right, so far so good. The final part, which requires just a little bit of pandas foo, is to cast the dictionary in a pandas series and then to sort values with ascending equals false, and that will do it in descending order. And what will give me is this pandas series view at the top. How many of you have a similar view if you did do pandas series? Just a quick show of hands. Okay, cool. And so the nodes are in the index, and the number of neighbors are in the column value. And node number 51 should be the one that you saw that has the most number of neighbors. So in this case, node number 51, node number 272, 235, 265, 195, etc. We might consider them to be perhaps important nodes of some kind, right? Okay, and I have that over here, so that's good. And there are multiple implementations. If you're curious about how they look, you can actually run the following cells over here. I have an original implementation and one that uses generators. This is kind of a little fancier. People who were at the time better than me at Python contributed some of those as well. So now let's talk about number of neighbors, and let's say we want to compare nodes. Say we had the exhibit, like this exhibit, the data that we have came from one particular day, and there were about 410, I think, people who came through the exhibit. But let's say we want to compare day 1 against day 2, and we want to compare let's say we also maintain node identities over the days, because some of the nodes that are present in that graph are actually staff members who are present across multiple days. And so now we want to go, well, okay, node 51 was present in this network of 409 other possible nodes with 2,000 plus connections. But what about to the next day, where there may be a different number of nodes and a different number of connections that were represented in there? Can we compare node 51 and its position relative importance within each graph? So it turns out the number of neighbors isn't exactly fair, right? Because how many neighbors, it's a combinatorial problem. If I'm present in a graph, how many neighbors could I have had connections with, right? Like it's every other node, so n minus 1, right? And so like if I were connected to 51 other nodes today out of 400, what about the next day when I was connected to 51 nodes out of like 2,000 people that came by? Am I still important? Maybe, maybe not. It depends, right? It depends on how the question we're answering. It's a little bit more nuanced than that. However, we might want to compare the normalized importance of that node, and basically that normalization factor would be dividing by the total number of people that are present. And this is how we generalize neighbors to arbitrarily sized graphs. It's that instead of merely counting the number of neighbors it has, we divide it by the number of neighbors that a node could possibly have, and that gives us one metric to rank order nodes, which is the degree centrality metric. All right? And so NetworkX actually provides that function for us. So you can do DCs, which is DCS, which is degree centralities, is pd.series of nx.degree centrality of g, and that will return for us the degree centrality of every single node that is present inside the graph. I can sort descending, and I should get the exact same order as before, right? Because it's a one-to-one relationship. So degree centrality returns a dictionary of key value pairs. The keys are the nodes. The values are the degree centrality metric. And so we can do the sorting. I did that already. So what I'd like you to do is to plot to do some little bit of graph statistics, right? And so this next exercise here is to visualize the distribution of degree centralities and degree distribution. So we're actually going to only do degree centrality because it's identical, basically identical code to the degree distribution. So what I'd like you to do is to do it for degree centrality, and what you should get is a plot that looks something like this. And I will explain once we're done with this exercise why I'm asking you to plot, why I'm highlighting the empirical cumulative distribution of the degree centrality distribution rather than asking you to plot the histogram. That'll make that point really, really clear. So please go ahead, attempt this exercise. Should be perhaps 2 or 3 minutes. And at the end of 2 or 3 minutes, I'll walk everyone through my answer as well. Okay, quick show of thumbs if you're done with this exercise. Yeah, I'm flashing up my answer up there on the screen in case you want to follow along, or if you're lost with a little bit of the API, no worries. That should help guide you a little bit there too. Give another minute or so. Okay, I'm going to walk through the answer with you all. Feel free to continue typing. First off, I need to get the degree centralities, so just the values, not the keys. So I take the nx.degree centralities of G and grab just the values. Then I cast it into a list just to be a bit more type safe and assign that to degree centralities over here. The next thing that I want to do is I want to calculate the XY coordinates for plotting the empirical cumulative distribution of degree centralities. And that would then give me X and Y values that I can either plt.scatter or plt.plot. Both will work. I don't mind whichever you use. It's just a difference in the thickness over here. All right. Thickness of the dots there. And then we plt.show within a Marimo notebook. So what do we see over here? I'm going to walk everybody through it. On the x-axis, actually, I'm going to do one more thing. plt.x label, degree centrality, plt.y label, cumulative fraction, and do that. All right. My high school science teachers would be proud of me for labeling my axes. You should always label your axes. Okay, so how many of you have heard of the empirical cumulative distribution function? Cool, some have. Most haven't, and I'm not surprised. It's not well taught in school. We don't see a lot of it. We actually see its ugly cousin, the histogram, for visualizing distributions. And I hate histograms. I want you all to hate histograms as well. We should not hate people. We should hate things. So let's hate histograms. Let's talk a little bit about what the ECDF really is plotting. It is plotting the distribution of degree centralities, which I have on the x-axis over here, by asking us to sort and order the degree centrality values, and then plotting on the y-axis what fraction of degree centrality values have this value or less, right? So then I can say, basically, 40% of degree centralities have a value of about 0.02-ish or less. The median, 50% of values, probably have 0.3-ish or less. The interquartile range runs from about 0.4-ish, which is that 0.75 to maybe about 0.25 down here. So the interquartile range is really about this regime on the x-axis, okay? What's the maximum value? Look at the top right-hand corner of the plot. That value is 0.12. What is the minimum value? Look at the bottom left-hand corner. It's close to 0, right? With an empirical cumulative distribution plot, none of your data points can hide. None of your data points can hide. That is the key. With a histogram, you can lie, cheat, and steal. With an ECDF, you have nowhere to hide. Let me kind of illustrate this point. Oh, sorry. If I were to look at this ECDF as well, what else might stand out to you? Oh, I love it. Outliers. Right over here. Whether they are actual outliers or not, we need to apply additional judgment. But those three data points are highlighted for us to see in plain sight. 4 data points, actually. You cannot hide anywhere. None of your data points can hide anywhere. Imagine what we did if we just played around with the bin size of a histogram. First off, I want to ask, how many outliers are there? Are there outliers in this histogram? Maybe? Did we, by chance, do we have n large enough that we, small enough that we might have by chance missed some of these values? Is it skewed in a certain way, right? That's another way to do it. Yeah, that's right. Let me switch the number of bins. Does that work? Come on, run. Oh, sorry, I have to run this cell down below. Great, okay, cool. Oh, I turned off reactivity. One moment, let me make this all reactive. On cell change auto run. Okay, I think that's the key here. So then, there we go, all right. I can lie, cheat, and steal with 2 bins. Are there outliers? not visible. If I go to 9 bins, are there outliers? Don't know. Are there obvious outliers? Maybe, but I had to change the bin size to see them. Do you see the point here? Right? Like don't use histograms because you can hide your data. You can hide things that you don't want people to see if you change the bin width. So the key weakness of a histogram is the bin width. I'll also note up here, the shape of the curve, there are characteristic shapes of curves as well. If I remember correctly, a perfectly uniform distribution should look kind of like a straight line, right? That means there's like equal numbers going like uniformly, they're uniformly distributed, because if you then integrate the area there, then you basically have it grow, if you integrated it, then that's how it would work. If you had a skewed distribution, it might, of edges, you might, or edge neighbors, it might look something like that, right? Where you'd have a very long tail. And if you had a very skewed, like if you had if you had a long tail to the right, then it would look something like, yes, this is long tail to the right, and then this guy over here would be long tail to the left. You have a lot of density that's on the right-hand side of this curve compared to what's on the left-hand side of that curve, all right? So this does take a little bit of adjusting to, right, to interpret an empirical cumulative distribution. And what's kind of interesting here is that the characteristic degree distribution of a graph tells us a lot about the property of the graph. And I think there are some graphs that have this scale-free property where the degree distribution shapes look similar regardless of the number of nodes that are present. That suggests that there's a similar data generating process for how connections are formed between them, right? And that's just something that comes out of the network science literature. So it's important to look at the degree distribution or the degree centrality distribution of your graph, because it can possibly hint at, if you do a comparative analysis between graphs, that can hint at to whether the graph generating process were the same or not. Okay, cool. Let's move on and try the Circos plot and arc plot. Actually, let me think here. With respect to time, I'm going to demo this for you all, and we're going to engage in the discussion rather than have you run through the exercise, because I think the NXViz API is less important than the discussion itself that we'll have about this graph. So I went ahead and I made the Circos plot of this particular network. What stands out? So I heard densely connected. Actually, Eric, can we get the microphone over to that gentleman over there? Maybe you want to elaborate a little bit?
It just looks like there's a gajillion nodes and they're all like connected to their neighbors. I can't quite see.
Oh yes, that's a good point. That's a very, very good point. I forgot to mention. Nodes here have ordering, and the order of the nodes is along the arc in this direction, and they start over here, and this is the first person to visit the exhibit. Then we go on to the next person out here, the third person out here, etc., and so on and so forth. So we are ordering the nodes according to the order at which people joined in on the exhibit. With that information, what else do you notice? The hand over on that side.
It seems like if there's a time progression here, that some people stayed longer than others, maybe?
Yeah. Yeah. Do you want to point them out? Actually, come over and up front. If you'd like to, come and draw on my screen. I think this makes it more fun. So put the pen down, and yeah, should be intuitive. And then if you press a little harder, oh, sorry. I'm going to do this, and press a little harder, and you can like draw that way.
Yeah, these people. So
Oh, don't press the button there. Sorry, just have to press down.
So it looks like this person who joined in here, they
Yeah.
were able to connect with this person who came in late, so this person
So there's
stayed
that.
a long time.
Exactly. So if I were to actually maybe even hammer home the point a little bit more, this individual out here, or this cluster of individuals here, appears to have connections that cross the arc, but also go with that in that direction and in that direction too. So it seems like there might be some highly connected individuals here. Great observation. What else? Any other observations? Are those cross time, long time arc connections abundant, or are they one of the sparser ones? I probably consider it sparser, right? Like it's not like we have a morass of edges that go like that and then like that and like that and like that and like that, right? Like we're not seeing a lot of long time arc edges. We're seeing them mostly being local in time, which is what you would expect for an exhibit with people moving through, all right? Cool. Here's an alternative to viewing it as an arc plot, and you can generate the visualization over here. It takes a little bit of time, and that's basically just unwinding the time axis. So you start from earliest to latest, and we see that same thing. Here are the people there are some people who have a long time arc. Who might they be? Staffers. That's a hypothesis. Are there others? Extroverts, okay, yep. Who else? They're not necessarily mutually exclusive properties. Yes, that's right. Any other possible hypotheses? Maybe they're infectious disease enthusiasts. They really like that exhibit. So visitors who love that exhibit, right, could be another one. Okay, cool. So those are some of the visual insights that we can get from, those are some of the visual insights. If you uncomment this cell over here, which has visual underscore insights, you can print out my answer and see it for yourself. Let me see what this is over here. I think one other exercise that would be really worth doing over here is to ask the question, is there a relationship between the degree centrality? Sorry, if I scroll down a little bit, is there an insight? Sorry, I need to rewind a little bit. So one of the things that we might have gleaned from the visualization is that nodes that have a high degree centrality might also be the ones that are responsible for edges that crisscross the circles plot or have long time arcs, right? And so we can actually do a data visualization to sanity check this idea, right? And the way that we might do it is we might plot on the x-axis the node's degree centrality versus the y-axis, the maximum difference between the neighbor's order and that node's order. And the order is an attribute of the node as well, as indexed by itself. So I'd like you all to give this exercise a shot. This one, granted, maybe a little bit foreign, but it's a way of measuring, are those with high degree centrality also the ones that are responsible for like lots of edges, long time arc edges? Not that they're responsible for lots of edges, but they're responsible for like long time arc edges. I will code along as well. That's wrong. Yes. 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 All right. How are folks doing with this one? Thumbs up if you're done. If not, we'll give it a few more minutes. Okay, we'll give it a few more minutes. It took me a little while to recall my answer as well. Okie dokes. I'm going to, in the interest of time, run through my answer. If you didn't complete it, don't worry. There's always a second chance, third chance. You can try this on your own at home. I'm going to run through the answers so we can get a flavor of what the solution looks like. First off, I mentioned on the x-axis we want to plot the degree centrality. So we need to get the degree centrality for every single node as a dictionary. So that's DCs on line 8 of this cell. And then for every node, I want to know what's the maximum difference between itself and its neighbors. And that's kind of the metric that we're going to use to correlate to see whether degree centrality and maximum amount of, the time span of that the time span of that person's presence, whether that was a correlated thing or not. And time span is bit quote unquote because we don't have exact timestamps, but we do have the ordering of the nodes by which they came in. And so we do need to loop over every single node, and we need to grab all of the neighbors. And since the neighbors themselves are integers, and the integers correspond exactly to the order in which the nodes came in, what I'm doing then is I'm just taking the diffs between those, I'm calculating the absolute difference between a node, a node itself, as well as all of its neighbors, so for each of its neighbors. And then I take the maximum value of that diff and assign it to the value of that node itself. And so node, say 7, might have a maximum difference between its neighbors of like 30 people. So it was connected at most to like people 30 time units, 30 ordered positions later. Then a little bit of pandas foo to make this happen. So I cast them as panda series, give them a name for both of those guys over here, concatenate them along the axis 1, the horizontal axis, the column axis, and then do a plot which looks like this over here. And so what would be a thing that we would describe? Like does that relationship hold true? That those who are present for a long time also happen to be the most connected? Maybe. It's not 100% guaranteed, right? There were some people who had lower degree centrality, but they were connected with folks that were, had a longer distance relationship in terms of the ordering. So that might be a different conclusion from just looking at this data. It's nuanced. Let me just put it that way. Or those who are on Facebook, it's complicated, right? So it's a bit more nuanced than a yes or no answer. But this is an example of the kind of questions that you can answer once you have distributions of metrics on a graph. You can then plot the correlation between the distributions and investigate whether they're correlated or not, right? And identify whether use that for further hypothesis generation to answer a particular question. Okay. All right. So in this notebook, we actually identified one measure of a node's importance, and that is the degree centrality metric. We looked at potential superspreaders and the likes in this contact network, or rather, not really superspreaders, it's more like people a lot of FaceTime with one another. And if this were to be an actual contact network, then we would say those might be the superspreaders. In other settings, the same concept might help us spot like influencers in a social network, or crowded airports with lots of connections, right? Like those which could be potential failure points in a transportation network, and many, many more other potential applications of identifying important nodes by calculating metrics such as the degree or the degree centrality. And so hopefully this was a helpful thing for you all to think about. So what we're going to do now, let me see. I think we should do a short bio break until 11, and then we'll come back and reconvene and do the Hubs notebook, which I think will be a intellectually challenging one. It'll be about 40 minutes for that one. So please go take a break, get refreshed and the likes. We had some good questions about scalability during the break. So I'd like to make sure that those questions were surfaced up. So your name, please, sorry. Keegan. Could you share your question, please?
I worked for a startup a few years ago, and they were trying to deal with graph data at scale. So they were using EMR, and they were using, I believe, GraphX or SparkX.
Yeah.
But networking component of Spark, and it's now deprecated. I'm wondering in 2025, what are the best practices? What tools would it be looking at something like Neo4j to process massive, terabytes of graph data?
Cool. And for that, to answer that question, Eric Welch, I'd love for you to come over to the mic here, so you're on YouTube.
I also have a mic here, but I'll be on YouTube. That's actually a pretty interesting and challenging question. What does scalability mean? Do you just want to have your data somewhere that you then can filter and aggregate? And some people still use Spark for that, or a pile of Parquet. If you actually want to do large-scale graph analytics, the SparkX package can be pretty slow, and so there are different scales of large. Is it like a million to million, like a billion, a trillion edges? So for the best scalability today, I would say is with cuGraph. And NetworkX, I'll talk about NetworkX backends in just a second, but cuGraph can run on multi-GPU. And they ran an experiment a few years ago where they ran PageRank on a trillion edge graph, that one with I don't know, a bunch of zeros in about 23, 24 seconds. And so like with GPUs, just the memory bandwidth, like, you can hide the latency and just get the bandwidth. And that's like highly, highly scalable. If you don't have GPUs or just can run on like a single massive node, there's also a technology called graph BLAS. This expresses graph algorithms in the language of linear algebra, and graph BLAS is like it does sparse linear algebra on a single node with CPU. GPU support is in the works, and now I circle back to NetworkX that hopefully you don't need to like switch and learn a new project just because you need to scale. And so I've been working the last few years on adding support for backends to NetworkX via dispatching. And so there is a graph BLAS backend. There's also a cuGraph backend, NX cuGraph, which runs on a single GPU, which can still be pretty beefy if you get the right one. And there are other backends as well. Like there's NX OrangoDB. OrangoDB is a graph database. They're kind of an everything database, including graphs. And they can like take their data and run directly with the cuGraph backend. I've also been working on NX Pandas backend, where so you can just have your data as an input of a Pandas data frame, and then that would convert. The plan is for that to convert to a different scalable backend. That's probably a very long explanation that's taken up so much of your budget.
It's all good. Cool.
Oh, great.
Thanks a lot, Eric. So for scalability, there's been a lot in the works. I definitely say one of the cool things about the evolution of the NetworkX package is that it started out as just pure Python, CPU bound, and intended for single node, no multiprocessing, nothing. It's just reference implementations of core graph algorithms, which, as we were discussing last night over dinner, it really is just like you can have an efficient algorithm, or you can have the more verbose and easy to maintain algorithm, and NetworkX will always choose in the early days, NetworkX would always choose the more verbose and easy to maintain algorithm, even if it wasn't the most efficient. But now with more people using NetworkX, there's interest in moving it, evolving it, and making it mature, not in the mathematical sense of like it's mapping to graph concepts, but mature in the engineering sense where it can now handle larger workloads through the dispatching and switching of different backends. So cuGraph, graph BLAS, et cetera, are examples of different backends for scaling out to larger numbers of nodes. We're talking millions to trillions, as well as larger numbers of edges, also in the millions to trillions edge scale. So hopefully that answered the question. Yeah, cool. All right, so we're gonna go on now to the next notebook. So let's close this guy up and close this. And now launch the structures notebook. UVX Marimo note edit sandbox 03 structures.py. And let's let that run, let that cook. Cool stuff. So let's run this guy. So in this notebook, we're going to look at how we can identify structures in a graph. So the previous notebook was all about like, if I were to look at the nodes and its relationships, which are the most important nodes? Now we're going to look at structures in a graph. And the first structure that I want to talk about is actually triangles. Triangles are super interesting, right? The way that I would think about it is that they are the simplest complex structure in a graph, right? An edge is trivial. But if you add one more node and you put two more edges between all three of those nodes, now you got the basis of complex structures that can show up. Okay, cool. So what we're going to do to learn about triangles, we're going to leverage another data set. We're going to switch data sets. We're going to go to a data set between physicians in Illinois, This data were collected in 1966. Sorry, this is 03 structures.py from 02 algorithms.py. So if you need to catch up, that's an exact notebook. An edge between two physicians, this one's important, shows that the left physician said that the right physician is his friend, or he turns to the right physician if he needs, to the physician on the right if he needs advice or is interested in a discussion. There always only exists one edge between two nodes, even if more than one of the listed conditions are true, right? So that's the description of the data set that we'll be walking through today. So let's load that up, hit Command Enter over there. First exercise, I'd like you to discuss with your neighbor, given what you know about thinking on a graph. So we did a little bit about that just now. How can you think of a few strategies to find triangles on a graph? So discuss with your neighbor for a minute. How would you find triangles on a graph? Okay, let's reconvene. Eric, can we have the mic ready? Who has some answer for how would you find out if a node is in a triangle?
I mean, we were thinking that maybe one way is if they are somehow in a undirected graph with each other, like three of them, for example.
Okay. So what would be the property then that would define that they are in a triangle in that case? Because I can have, I can have a node here and it's connected to two neighbors, and that's all undirected, but that's not a triangle. Okay, Ariana at the back. Let's. Oh, okay, good.
So I get the set of nodes that I am connected to.
Right. So all of my neighbors.
Yeah. So I have a set of nodes, like whatever, a handful.
Yep.
I compare and see within all of those if they are connected to each other.
Okay.
That's automatically a triangle.
Yes. So if any of your neighbors are connected to each other, you are automatically in a triangle. Yes. Mike.
Sorry. If you have you can only have a certain number of triangles from each node, so you can kind of keep track of how many triangles you're a part of.
Right.
And then you can eliminate, possibilities if you have a very large set of nodes that you're parsing through.
Right. So if you have lots of neighbors, it's combinatorial n square, which is the number of possible triangles that you could be part of, right? So that's an important point to think about.
Does that capture when the third nodes link back to the first node?
That does, because if the set of nodes that I'm considering are already my neighbors, so if I were to try to draw it out, this one is going to be a little bit challenging, but if I were to draw it out, I got to be fast on the ground for this one. It disappeared. Okay, picture in your head, that one failed. Picture it in your head, you've got yourself and your neighbors. So by definition, I already have connections to them. And if my neighbors are connected to one another, that forms a triangle. So my elbows are my neighbors right now. So that already covers the situation where I might think of it a different way. I go to my neighbor and then go to my neighbor's neighbor and ask if I'm in my neighbor's neighbors, right? And that's another way of approaching the same problem as well, which I think some of you also would have settled on as well as the answer. So those are they're equivalent solutions basically. One involves an n-square comparison of all of your neighbors, and the other involves a depth-first search through your neighbors. So then, you would have to do your second-degree neighbors. Yeah, you'd have to go to for each of your neighbors, you'd have to go to your second-degree neighbor and then ask if you're a neighbor, right? So there's a little bit of complexity there too. Yeah.
Comparison.
Mike.
Like, if you have many neighbors, so you are exploring and comparing.
Yep.
The connection.
Yeah, that's right. So if I had many neighbors, right, then I would be spending a lot of time comparing pairs of my neighbors if I were to do the first strategy. And if my neighbors had a lot of neighbors, then I would spend a lot of time on the depth search of my neighbors, right? So trade-offs between those algorithms. Okay, cool. So that's pretty much the strategy that we would go for. So that's the triangle finding strategy. So I'd like us to try to implement the in-triangle algorithm. So that's the first exercise for this notebook. Please give that a shot. And I am going to also code along with everybody. Alrighty, I'm going to very briefly walk everyone through one of the two implementations. This is the one that checks if my neighbors are connected to each other. The criteria here is I just want to know if I'm in any triangle. So if I find the first, basically the logic here for this function is if I can find the first triangle that I'm in, then I'll return true. If there's no triangles, then I return false. So the way that I'm choosing to approach the problem, we start with from itertools import combinations. And that allows me to create an iterator over the combinations, the pairs of my neighbors. I'm going to zoom in a little bit. And then basically I do for neighbor 1, comma neighbor 2 in the pairs, so combinations of g.neighbors of that node, comma 2, that gives me all pairs. And then if I go, if has edge neighbor 1, neighbor 2, then I return true. Otherwise, I return false outside of the loop. Because if the loop completes and I found no triangles, then basically by definition this node is not in a triangle relationship. And I can verify that it is correct by executing this cell down here. So command enter, 21 milliseconds to execute. I do a random sample of like 10 nodes and just check if it is in, if it matches what is available with the nx dot triangles, G over here. That test looks really weird. I'm going to have to modify that test for the future because it looks a little weird to my gut. I can't tell exactly why right now because we're live in a tutorial session. But if you find other nodes that are not inside a triangle, then they should match the nx.triangles function as well. Okay, cool. So now what we're going to do next is we're going to extract triangles for plotting because I think it's useful if you've identified that a node is in a triangle relationship. Maybe we would like to plot those. So the prompt for this next exercise is given a node, write a function that extracts out all of the neighbors that it is in a triangle relationship with, and then in a new function, implement code that plots only the subgraph that contains those nodes. And so you may need to use g.subgraph over here, and I will code along with everybody. So please feel free to take a few minutes to do these two implementations. Can reuse functions. No, we cannot. Yeah, I need to do this again. Okay, I'm going to briefly walk through the solutions. As always, feel free to catch up afterwards. Let's make sure we more important thing is that we get the gist of how it works. So first off, we have triangle neighbors. Getting triangle neighbors, and the goal here is I want to, given a graph and a node, I just want to extract out the nodes, the neighbors in which that node is in a triangle with, right? So not all of the neighbors, but the subset of neighbors only. So we'll do something that's similar to the previous, in triangle implementation where we iterate over pairs of neighbors. Let me scroll back down to here. And what we do is we ask if there's an edge between neighbor 1 and neighbor 2. Then we add, I have a slightly wrong implementation. It should be add neighbor 1 over here, and we add neighbor 2 into the set. And then finally, we return the triangle neighbors. So that gives us, excluding the node under consideration, it gives us the neighbors with which that node is under in a triangle relationship. And then we can reuse that function, get triangle neighbors, to get within the plot triangle relations function. And what we would do is we'd get the triangle neighbors, add back the node, and finally do a subgraph of just the triangle neighbors with itself. And finally do an nx.draw over here. And let me just see, did I get that right? plt. Oh, yeah, I need to do that. There we go. So nx.draw should give me that. In my actual answer, I have the node labels also added on. So we can probably do that. Let me see. Labels equals true. I think that should do the, that doesn't work. I forgot how to do it, NX API, but it is possible. The answers are in the solutions has the answers as well. So you should see something that looks like that. Thumbs up if you got it. If not, no worries. There's lots of time to go through it. The more important piece is that we know how to iterate. We know the logic for finding triangles. So why are triangles so important? Like, we've spent a lot of time on them. Well, it turns out, how many of you know about the earliest fabled implementation of LinkedIn's friend recommender? Yeah, it's a pretty cool story. Like, the idea here is, if A and B are connected and A and C are connected, then perhaps there's a chance that B and C should be connected. And if I have A being connected to B and A being connected to C, and also A is connected to, like, another person is also connected to B and C, and yet B and C are not connected, it feels like that would increase the odds that we should just recommend people to connect on LinkedIn, right? So the logic goes that triadic closure, this is what they call triadic closure, is kind of the one of the earliest algorithms that were in place for recommending whether two people should be recommended as a friend connection or not, right? So that's one of the more practical applications of, say, finding triangles and the likes. Any questions so far on this triangle finding exercise and the likes? No? Yes? All good? Cool. Let's move on. Right, so that's the triadic closure algorithm, and that's the text for triadic closure. We sped run through that because of the interest of time. I'm also going to skip getting open triangles. Let me think here. If we go do this one, I'm just going to really quickly, yeah, actually, I would like to skip open triangles because I think open triangles is an extension of the logic of finding triangles themselves. Basically, it's the flip side, the opposite. So if you'd like to try that at home, give that a shot. I think the next one that's really cool is finding cliques in a graph. So let me scroll down to where the cliques are. The cliques section is. So cliques are the next, they are the simplest clique, complex clique that can exist. And the definition of the clique, by the way, is that it is a set of nodes in a graph that are fully connected with one another by edges in between them. So if we take this definition of a clique, what is the simplest clique that is possible? One edge. Who said that? Yes, that's right. One edge. An edge is a simplest clique because it satisfies that definition, but a simplest complex clique would be the triangle. And in fact, we can generalize this to this concept of k cliques, which is the number of nodes that are involved in a clique. So an edge would be a 2-clique, a triangle would be a 3-clique, a square with crossover connections would be a 4-clique, et cetera, et cetera. And so this over here is what we mean, yeah, that's the 4 cliques, the k cliques concept. And then related to the k clique is actually this other idea called a maximal clique. And it is defined this way, which is a subgraph of nodes in a graph to which no other node can be added to it, and yet that set of nodes still remains a clique. So that would be considered a maximal clique. And NetworkX provides us a way to find all maximal cliques, and it is through this API call called find cliques. And it would look like this, and basically you would get back an iterable of all cliques that are present, and the members of the cliques are what we see over here. So for example, node 1 and 2, nodes 1 and 3, those nodes 1 and 2 are in a maximal clique, so that edge is a maximal clique, that edge is a maximal clique. This is a 4 clique, that is a maximal clique. One of the reasons why we think about finding maximal cliques is because by definition, if I have a 4 clique identified, I have identified all of the 3 and 2 cliques underneath it. Think about that. Because a clique is fully connected, right? So if I have a 4 clique, I've also already fully identified the 3 cliques underneath the hood, and I've identified the 2 cliques or the edges all underneath there. So if you can find a maximal clique of a certain size, you'll have by definition found all of the k, less than k sized cliques as well. So what I'd like you all to try as the next one is to write a generator function. So this one should yield and not do a return. Write a generator function that yields all maximal cliques of size k using the NetworkX API. I'm going to pair code it up myself as well, and then give a little bit extra time for folks to try out the exercise. If you don't finish it, don't worry. Like, this is the idea. I just want this idea to be available for you all in your mind. So let's try this. Okay, so just to walk through the idea with everybody, we use find cliques from NetworkX to find all of the cliques, but then we iterate over them. And if all we need to do is check that if that clique is of a size k, then we yield it, and so then it becomes part of this function then becomes a generator. One of the reasons I want to talk about this is because if you have graphs in memory that are pretty large, one of the patterns within NetworkX is that to help with memory consumption, some of the functions are actually implemented as generator functions rather than like stuff that return, and so that can help with a lot of the memory consumption of the graph. Because I've worked with NetworkX graphs before. My thesis had like 16,000 nodes and lots of edges inside there, and that graph, in its naive form, object form at the time, needed the use of an HPC cluster for me to manipulate it, until later when I figured out how to do this all with matrices, which we'll talk about matrices later. All right, so far so good with that? Okay. Clique decomposition, I'm going to skip because I think we went through that piece there as well just now, which is basically the idea that if I have a k clique, I have all of the k minus 1 cliques recursively all the way down to the 2 cliques. So you think about if I have a triangle, by definition, that's a 3 clique. I basically also have the 2 cliques present. So if I have a 4 clique, I have all of the 3 cliques also present. I can do clique decomposition. So we don't need to harp on that too much. The other part that we wanted that helps us identify interesting structures in a graph are connected components. So connected components are, to help illustrate that, I'm going to draw the graph that we have over here. And this is drawn as an arc plot, perhaps popcorn style. What do you all see? Seems to be, are there disconnected groups? Yeah, seems to be how many of them? 4 of them, which roughly corresponds to the cities, the 4 towns in Illinois that were being, for the physicians that were being studied here. So each of these 4 subgraphs that are disconnected from one another, there's a name for them, and it's called a connected component subgraph. And so NetworkX also does have a connected components API that will allow you to view how many connected, that will get you the number of component subgraphs that are present. I am going to redraw that plot with a thing that, sorry, let me back up a little bit. I'm going to first find a way to visualize the connected components. So what we're doing here is we're labeling the graph. This is an example of like what Eric was mentioning, which is you take a graph, you compute some properties of it. And so in this case, I'm computing a categorical property, which is like which connected component subgraph ID am I part of, right? And I take that information and I annotate it back onto the graph. So that returns for me G labeled. And if I do G labeled dot nodes, data equals true over here, you'll notice I now have metadata that is basically subgraph 0, subgraph 0, et cetera, et cetera. Where do I go to subgraph 1? Probably all the way out here. Subgraph node 155 is now part of subgraph 1. So this is me labeling each of the connect nodes according to which connected component subgraph it is, and it's a way of computing a property of the graph and then annotating it back onto the node. And then I can plot the connected component subgraph this way, where basically I have I have them grouped by their connected component subgraph out here, and you can see based on the graph visualization that the connections indeed are just within a particular community. And this would make sense for the 1966 world. This probably would not be the same connected structure in 2025, right? What would be your priors on what this would look like in 2025? Oh yeah, I see Ariana just going like that. That's just be all over the place, right? Like that's 2025's trust network is different. Okay, cool stuff. Let me just see here if there's anything else. We can do the same for arc plots. I don't think that's particularly important, that we went through as well. Any questions about finding interesting structures? Aaron in the back. Let's get the mic, Eric.
So these subgraphs only work when they're completely disconnected, right? There cannot be a single connection. Is there any, like, I can imagine situations where I would still want to know that like 99% of the nodes are in one cluster and one physician is talking to their brother in a different city or something.
Yeah.
Is there any way to know that? Like, how can we say like how clear these groups are versus how like fragile they might be, or how many nodes? Like, is that a thing?
That is a thing, and it relates to community detection. Right, and so in that particular situation, we would label, say, that big group 0. Let's say there was this big group 0, and we just so happen to have one physician talking in this direction over here, like this. So now suddenly 0 and 1 together with this extra node, with this extra edge, are a connected component subgraph. But if we were to do community detection, we might actually decompose them back into groups 0 and 1. And that is different from finding connected component subgraphs. So connected component subgraphs are perhaps the most vanilla definition of a community. Community detection algorithms actually apply statistical tests that ask, is this node, and it's like, is this node a member of this community more, is this node more likely a member of this community than another a community based on its connections? And there are statistical tests that some automated community detection algorithms do. One of the co-authors of the tutorial, Mriddle, he's a fan of the Louvain. I don't know how to pronounce that in French. I'm not a francophone. Louvain community detection algorithm, and there's actually a Python package for that, and it works with NetworkX graphs. So that's one to check out. I think NetworkX itself also comes with a few more basic community detection algorithms as well. But community detection is the name. Cool.
NetworkX has Louvain.
Oh, NetworkX has Louvain now.
Yes.
Okay, I'm a little bit outdated. Thanks a lot.
It also has Leiden as a backend only. It's
Yes.
going to implement Gliden, but some backends implement Leiden.
Okay. So the Leiden and Louvain are both implemented. I have a question over there.
My question is not directly related to what we've just talked about, but like the network packages you use. So in the past, I've used iGraph, and I noticed here I used NetworkX a lot. I was wondering why you chose this package, or if there's other packages you've tried out that you have liked also.
Yeah, so iGraph is an alternative to NetworkX. Its API is, it's written in C++, if I remember correctly. It has Python bindings. So generally, iGraph for single node computation has been noted as being faster than NetworkX. I did try to pick it up back in the day. This was 2015 when I was trying to decide what should I actually implement my thesis on. And so I did it in NetworkX primarily for the friendly API, more so than anything else, and the extensive documentation, which speaks to the practice of documentation, by the way. Docs are so important for open source projects. If you happen to be hanging around for the sprints, and you want to sprint with any of the open source projects that are going to be sprinting, docs are a great way to get into the game. So go forth and doc. It's a great way to do it. So, but anyways, back to your question. Docs were documentation and friendly API were the main reasons. And I'm glad now, of course, there's engineering work that's being done to help with the scalability aspect as well. Cool. Any other questions? Okay, I really love the engagement and discussion today. This has actually been way more than I've ever had at any SciPy tutorial. As a result, though, we're not going to be able to go through the one notebook that would have fried everyone's brains before lunch. That is the one on doing pathfinding algorithms. So what I'm going to do actually is I'm going to give, in the last 10 minutes, just a very brief monologue about like what the following notebooks are. And that will give you a bit of an intro for yourself if you want to work through them at your own pace on what you can expect to see from those notebooks. And then I will end up being the only thing between you and lunch, and I will make sure that to the best of my powers possible, we're going to make sure you're going to go for lunch on time. We went through paths and then, we went through structures first, didn't we? Yeah, okay, I skipped notebook 2. So let me open up notebook 2. Paths.py. We skipped that one, and perhaps it was a little fortuitous, so no one has to walk into lunch with a fried brain. This notebook is really about finding important nodes as defined by pathfinding algorithms. And what do I mean by that? It means this. Yes, I might be a node that is tightly connected, highly connected to other nodes. But in a graph where there's transmission of information across nodes, there may be critical nodes that exist that do not have a high degree centrality, but yet bridge between 2 communities or 3 communities. Those nodes tend to be very important nodes for the purpose of information spread or the spread of anything on the graph, right? And so those nodes happen to be high betweenness centrality. So through notebook 2 on paths, what we do is we actually try to implement the breadth first search algorithm, which is why it would fry everyone's brain. We try to implement the breadth first search algorithm to look for a path, to determine whether a path exists between any pair of nodes, right? And if a path exists between any pair of nodes, then nodes that are along that path may be important because there are paths through them that exist between any pair of nodes. And that is the definition of betweenness centrality. If you have time at home, I'd strongly encourage, most of my, all of yesterday's tutorial at Building with LLMs, I was like, use AI, go do it. Like, don't cheat, don't cheat. Go cheat, go use AI to help you. I, in fact, used AI to help myself live during the tutorial. But for this exercise, just this one exercise for implementing breadth first search, don't cheat. Trust me, it is such a satisfying exercise to run through. When I was in grad school and very unskilled with programming, it took me 3 hours on a whiteboard to figure out how to do the breadth first search. I was very unskilled at the time. But once I got it, something clicked. And so if that represents you right now, I'd strongly recommend go back, take some time, try to implement breadth first search inside this notebook. You will have a very satisfying time making it happen. What it will teach you is how to think on a graph, right? It comes back to this idea of like with the visual cortex, a human can map out a graph and just go, is there a path between these nodes? Yeah, do that, and there's the path. Is there a shortest path? Do that, and there's the shortest path. But a computer doesn't have that visual cortex. So in order to do that, you have to operate as if you were locally on the graph, on the node itself, looking at the neighbors, keeping track of stuff in memory, and moving to the next node, etc. That is a very useful skill for algorithmic thinking. Strongly recommend, don't cheat on this one. Try to make it work from scratch. If you fail the first time, which is what I did, do it again the next day, the day after, until it really sticks and it like the pain hurts and burns the algorithm into your brain, right? Like that is the one thing that I would really strongly encourage. So that is the notebook on paths. If I were to move over to the next directory, the practical notebook, the only one I would recommend from this, UVX Marimo 01 io.py. This notebook, what is this notebook about? This notebook is about some of the more practical aspects of reading and writing graphs. The last thing I want you all to do is save your graphs as pickles, so please don't do that. It's a security hazard. Your cybersecurity team at your company will come chase you if you do that. On the other hand, if you want to load graphs from disk, there are ways to do it using pandas data frames, and that is what this guy is all about. You can actually represent nodes as tables, and you can represent edges as tables, pandas data frames. As long as you have columns that correspond to the nodes in the node table, or pairs of columns that corresponds to pairs of nodes in the edge table, every other column can be considered metadata for the edge in the edge table or for the node in the node table, okay? So that's the most practical thing to take home from the I/O notebook. How do you read graphs and save graphs? I do end up cheating and saying if you save a graph as a pickle, just don't email it to someone else, please. Right? Like that's a bad idea. Don't share it with other people. Use node and edge tables as the canonical format. And if you have really, really large data, save it as like a Parquet file or something. That's binary format can work. I think I got a question.
No, it's like, can you elaborate why it's a problem?
Why pickles? Yeah, why pickles are a problem? It's because pickles, if they come from an untrusted source, if you don't know what's inside there, every time you read a pickle, you can execute arbitrary code that's associated with that pickle file. So it's a security hazard. Don't do it. All right?
Wasn't there historically certain graph files, like it used Giphy, like 10 to 15 years ago? They had specific files, like you could export. Originally, like Facebook had an API before they locked it down, where you could export into certain files. Is there a certain format that's still used today, or do you still recommend just using Parquet?
I just recommend Parquet nowadays, because if you needed to do other types of analytics on the node table or the edge table, it's just readily available. So then you can read from Parquet into Pandas data frames, and then read from Pandas data frames into NetworkX graphs that way. So hopefully that answers your question. Okay, and the final thing that I thought would be really cool for you all to look at is in the 04 advanced notebook. We go to 02, the LinAlg notebook is the one that I'd like to show you all, because some of you all asked about the scalability of certain algorithms. And in this notebook, all the way at the bottom, let me just see here. Where is it? Where is it? Where is it? Where is it? Okay, right here. In this notebook, all the way at the bottom, there is an example taken with real Amazon data that was published of customer product graphs. So this deals with bipartite graphs to begin with, and secondly, it then deals with projections onto calculating similarity between customers based on their purchases. And what's really cool here is at the bottom, we show two implementations of taking bipartite graphs and projecting them onto one partition, one using the native NetworkX API, and I think this is running. It's finished running already. Right, it's finished running. Okay, my machine, I no longer have a MacBook Air, but a MacBook Pro, so this thing was fast, but when it was on my MacBook Air, it would take this algorithm, which for sense of scale, I think had 1 million nodes and roughly 1 million edges inside there as well, to calculate the projection, which is to say, find me the customers that are most similar based on their shared purchase history, right? The projection from the customer to purchase graph to then just the customer graph. That in Python API land is 3 seconds, 16 seconds if you're on my old computer. If you do this and express the entire operation with linear algebra instead, it is 0.4 seconds, so 10 times faster minimum, right? To take this to express an algorithm from object-oriented form into linear algebra form. And this speaks a little bit to what Eric was saying about GraphBlast, which seeks to implement certain graph algorithms in linear algebra form and then as such achieve a speed up over there. So this one's a really cool notebook to look at if you do probably want to run through the bipartite graph notebook first, just to make sure you understand bipartite graphs, and then you can take a stab at this one afterwards. So that's the brief introduction to whatever is left for the most interesting parts of this tutorial series. There are also 2 case studies, one on airports, one on Game of Thrones, that Mriddle, my co-author on the tutorial, he put up there. And if you're interested in those are also cool for learning, and applying some of the concepts that are listed inside this tutorial series. Thank you so much for coming. If you got feedback, I'd love to hear it. Otherwise, enjoy the rest of the conference.